Good morning, everyone. Before I start, I just want to make sure I'm audible. So please let me know in the chat box if you can hear me clearly. Okay, thank you. So this is the third session on trees. I'm assuming that you're familiar with what we have discussed in the last 2 weeks. The agenda today is to take up a collection of tree problems that can be solved using a particular subtype of depth first search, which I had called as bottom-up depth first search last time, as well as post-order depth first search. So if I quickly go back to um, a slide from last time. So this is from last week's slides. We talked about top-down depth first search last time, and I mentioned that depth first search in general or depth first traversal of a tree in general is another way to think about solving trees problems using the decrease and conquer strategy. Breadth first search is something we had seen in our first session, and last week we saw that given a tree problem, as a lazy manager, instead of thinking about digesting the entire problem, you ask the question, uh, if I take the for the root node of the tree and figure out a way to two subordinates, right? A left subordinate who would be given the left subtree to tackle, and a right subordinate pass down a modified subproblem definition for them, and potentially some information that they may need in order to work on their subproblems. Me to my two subordinates, and because they're going to be equally lazy like me, they would solve these subproblems in exactly the same way. So this is what I had called as pre-order depth first search, because I do some work up front and then I pass down these subproblems to my two subordinates, and then I am never involved in solving this problem from there on. So I can go on vacation. I know that the work's going to get done, because what is ultimately going to happen is that the leaf level workers at the bottom um, who um, get the smallest possible subproblem to solve, they would solve a bunch of these subproblems at the very bottom, and they are the ones who actually have all the data needed to contribute to the solution, right? So collectively the leaf nodes solve the problem. So they all have independent access to a global mailbox lying outside the office. They can go and make changes there, and finally it's in that global mailbox that we find the solution. So that was top-down or pre-order depth first search. The basic depth first search code that we had seen last time was the following. So we had like an edge case similar to what we had in breadth first search, but the work done by an arbitrary internal node manager is what we had codified in the form of this red box inside the body of this helper function code. So the subproblem definition would be that each node is going to be given a subtree. So whichever node is the entry point to that subtree, that would be passed down to them, potentially with some additional information coming from above. And the delegation would happen by means of these two recursive calls. And in pre-order depth first search, the work would be done, the work by the manager would be done here before making those two recursive calls. Today, we are going to look at post-order depth first search, where the work would actually be done after those two recursive calls. And instead of passing down information to the subordinates, we're going to see that in post-order depth first search, the work done by the manager is going to happen in a post-order fashion. So if you recall the tree traversals, the three kinds of tree traversals, pre-order, in-order, and post-order. In post-order um, traversal, when the depth first search code runs and it builds out this entire uh, tree, and the chain of recursive calls and returns from those recursive calls follows this kind of boundary walk that we had seen last time. What happens in post-order depth first search is that you have to imagine uh, these protrusions sticking out on the right side of every node, marking internal nodes in, well, every node. But so for internal nodes in particular, when the boundary walk uh, reaches them from the right side, what would have happened is the two subtrees, the subordinates who are responsible for the two subtrees, they would have already solved their respective problems. And so when we hit the right protrusion at any internal node, the manager has the information that has percolated up from the two subordinates um, in the form of return values. So we're going to have return values from these two recursive calls now. And using those two return values and the information in that node, each manager would compute their contribution, their local contribution to the global solution. And they would have access to that global mailbox outside the office. And so the actual solution that will be built up is not going to be built up, or is not going to be finalized by the leaf workers at the bottom, but by the upper management, because they are going to need information from their subtrees in order to construct the solution. So you can say that it's really the root manager at the very top uh, who is going to, you know, put the final nail uh, in the mailbox. Uh, in other words, finalize the global solution in most cases. So that's how the structure is going to be different of the traversal. It's very similar to what we had done last time. It's just that we're going to need to do the work at the end. And as we take up problems, individual problems, we'll see, how do we decide between pre-order and post-order. Okay, so that's just a review of what we did last time, plus where we are heading today. Oh, my voice is breaking. Is it still breaking? Okay, not anymore. Okay, good. Is there anything you want me to repeat, or um, like, do you think I need to repeat what I said? The initial parts. Okay. So in the initial part, what I what I just said is depth first traversal is a way to um, it's a way to solve a tree problem by really relying on the recursive definition of a tree. So a tree itself can be defined as nothing but a root tree node with two children, and both those children themselves are trees. So a tree can be empty, it can be a single tree node, or it can be a node with up to two children, and both of those children are themselves trees. That would be the recursive definition of a tree. And so any problem on a tree can also be followed by relying on this recursive definition and using a decrease and conquer approach where the root manager decides to do a little work. It could be at the beginning, in which case we call it pre-order depth first search, or it could be at the end, in which case we would call it post-order depth first search. I'm going to leave the third subtype of depth first search for a future session. So today we're going to look at post-order depth first search. So is that okay? Is there anything that you want me to repeat um, or explain again? Okay, fine. So the problems from the last meeting are there in the slides. Please take them from operations. I'm going to focus on what we need to do today, which is uh, these problems. And so let's begin with the first problem, the problem of figuring out whether a given binary tree is balanced or not. So given a binary tree, we want to determine if it is height balanced. And what does it mean to be height balanced? Um, what it means to be height balanced is that the difference between strange, it looks like they have eliminated the definition of what it means to be height balanced. This used to be more elaborate earlier, but let me just write it down. What it means to be height balanced is um, for every node, the difference in the heights of its left and right subtrees is at most 1. So this specific definition of height balance leads to a kind of um, balanced binary tree called an AVL tree. I've taken a class on AVL trees um some time back. You can watch the recording of that if needed. So there are different ways to to define what the word balanced means. This is one particular definition. So in this toy example, this binary tree is balanced. Why? Because you consider every node, right? Let's start from, well, let's say we look at the root node. What is the height of the left subtree? So let's say we define the height in the same way that we had last week, which was uh, how many edges, or sorry, um, how many vertices are there from the root to any leaf, right? If you consider any path from the root down to any leaf, and you look at the longest such path, the longest such path would have a length that's equal to the height. So this has a height of 1 because there's one uh, node only in the tree. This tree has a height of 2 because if you look at any root to leaf path, the maximum length of that would be two vertices. Another way to look at height is if you call this as level 1, if you call this as level 2, uh, look at the leaf with the maximum level number. Right? That maximum level number would be the height. So here the height is 1, here the height is 2. And so the height difference between the left and right subtrees is 1. And so it's okay to have a height difference of 1. It shouldn't be 2 or more. Right? The height difference can't be 2, 3 or anything more than 1. And this should happen at every level. So when we look at this node in particular, it has a left subtree and a right subtree which are both empty. So the height difference is 0. So this node is also height balanced. This node is also height balanced because it has two subtrees and both have a height of 1, you can say. So the height difference is 0, and that satisfies this definition. Every leaf node is going to be height balanced because the left and right subtrees are both empty. So the height difference is um, within 1. When we look at this second example here, so let's consider this root node here. It has a right subtree that has a height of 1. It has a left subtree. What is the height of the left subtree? So we have level 1 here, level 2 here, and we have level 3 here. So the maximum level number we see in that subtree is 3. So the height of this left subtree is 3. The height difference between the left and right subtrees is 3 minus 1, which is 2. 2 is more than the allowed limit of 1. And so this tree is not height balanced, even though there are individual subtrees within the tree which seem to be height balanced, like this particular subtree is height balanced. Even this particular subtree we can say is height balanced because if you look at the root node here, it has a right subtree that has a height of 1. It has a left subtree here which has two levels, so a height of 2. And so 2 minus 1 is 1. And so if we were just given this subtree, we would say it's height balanced. But when we look at this node here, um, that node does have a left subtree that has a height that's too much. Uh, the third example here is of an empty tree. So in many cases, we don't know what answer should be returned for an empty tree because you could argue both ways that in one sense it's height balanced because the left and right subtrees both have um a height of 0, or if they don't exist, we assume they have a height of 0, and so you take the height difference, that's 0. But in another sense, one could equally argue that, well, we should say this tree is not height balanced because there isn't even a tree for there to be balance. So we just go in such cases with which whatever definition lead code prefers, and that's why it's good to have a separate edge case for an empty tree because sometimes the answers that are expected for them um, may not match the general pattern. And so having separate edge case for an empty tree allows us to return that special value. So the number of nodes in the tree is from 0 to 5000. 0 means it could be an empty tree. Okay. For any questions about prior classes and their recordings, please um, ping Ayushman on Discord. So how do we start thinking about this problem? We want to determine if a given binary tree is balanced. And so we want to think of ourselves as the root manager who has been given responsibility for the entire tree. We potentially have a left subtree and a right subtree, both of them, although it's not necessary, but in the general case, both subtrees will exist. And so we want to determine if the entire tree is height balanced. So the global problem I'm given is um, um, is the entire tree height balanced? But being lazy, I'm going to just do the bare minimum work um, to um, not solve the whole global problem, but just what can be solved at my level. So I need to define a local problem that I can solve such that if I solve that local problem and every manager in this tree, every node in this tree solves the same local problem, then collectively we could aggregate the solutions to all those local problems and solve the global problem. So the local problem that I can try to solve uh, most naturally is, um, am I height balanced, right? At my level or at my node, is my node height balanced? I am taking responsibility only for one node, following a decrease and conquer thought process. Is my node height balanced? So if my node is height balanced, and if all other managers in the tree determine that their nodes are height balanced, then the entire tree would be height balanced. But even if there's one uh, manager in that entire corporate hierarchy who determines that their node is not height balanced, then the entire tree would cease to be height balanced. So a single false answer from any of the managers would make the overall answer false. So note that this is a decision problem. The answer to this problem is either true or false. And so these local problems also have a true false local answer. And we can actually say that the global answer is going to be the AND of all the local answers. So all local answers have to be true for the global answer to be true. Even if there's a single false, that will render the global answer as false. So the question is then, how do I solve my local problem? How do I solve my local problem? So if I draw a generic tree and let's say this is where I am, I have to think from the perspective of an arbitrary internal node manager in the corporate hierarchy. What I am asked to do is to solve this local problem. Is my node height balanced? So to answer that question, I have to look at the subtree rooted at me, right? This subtree is what I focus on to determine my local answer. Now, is this something that I can solve by just passing down information to my leaf nodes? Well, not really. If you think about it, in order to determine if I am height balanced, I need to know the height of my left subtree and the height of my right subtree and verify that the height difference is at most 1, right? That is the definition of being height balanced. So if I just purely pass down information down, to my two subordinates and they do the same thing, then the individual leaf nodes at their level are getting, perhaps they can determine the depth at which they are, right, their level numbers, but they can't really solve um, the problem on their own, because they need information from about other paths, how deep are all other paths, in order to figure out what's the height difference. But this is something I can do at my level more quite easily if I had the answer to what is the height of my left subtree and what is the height of my right subtree. So when I need information about um, both subtrees, I need information from about both subtrees rooted at me, then that information is something that's going to have to be passed up to me by my subordinates. It's not something that can be solved by just passing down information to my subordinates. I have to integrate information from both sides, right? That's the simplest way to think about it. The very definition of height balance requires me to integrate information from the left side and from the right side. And so it makes sense for us to use an approach where that information from the left side and right side are both available to me before I can proceed and do whatever local work I'm uh, assigned to, whatever local work I've decided to do. So the information has to flow up to me. And so that is what pushes me in the direction of using bottom-up depth first search or post-order depth first search. So, so how are we going to write the code then for this? So the information I need from both of my subordinates is what is the height of your subtree? Once I have that information from both sides, I will have the solution to my local problem. The catch here is that if I need that information from my subordinate, I also need to pass that same information up to my manager. So it's very clear that the return value from my subordinates, which was the height of the subtree, is also going to be my return value to my manager. Right? Everyone has to be running the same code. If my subordinates are passing up the height of their subtrees to me, that requires me to do the same thing for us to collectively solve the problem. So it seems like I have a dual agenda here, right? I also I also need to pass the same information up to my manager, plus I need to solve my local problem using um, the information flowing up from my subordinates. So every problem, um, in general is going to have this dual agenda. I, I need to pass the appropriate information to my manager, which I am expecting from my subordinates. And I need to use the information my subordinates passed up to me to solve the local problem. And update the global answer. And update the global answer using that local answer. Right? For example, I know that the global answer is going to be the AND of all the local answers. So if I find that my local answer is false, then I have determined the global answer. So I can go outside to that mailbox and set it to false. And if any of the employees sets the global answer to false, then it's going to permanently remain false, right? Even if um, some of the managers who compute their local answers later find that the answer is true at their level or at their node. If a height imbalance is detected anywhere in the tree, then the overall tree uh, lacks a height balance. So when we write the code, we are going to do it in two stages. We'll focus on these two items separately and not mix them together in our thought. Okay, so and it's very clear how I'll solve this. I'll have two return values from my two subordinates, and I'll just take their difference, right? The absolute value of their difference. If that answer is less than or equal to 1, my local answer is true. If that answer is false, then my local answer is false, and the global answer is also going to be false. The first um, uh, sub problem that I need to solve. Uh, well, my sub problem is this local problem, but the other action item for me is to make sure that my manager gets the required information from me, which I got from my subordinates. So I need to use the height information from my two subtrees to compute my own height and pass it up to my manager. And you can expect that, I'm adding an extra level to my subtree. So whatever the bigger of the two heights is on either side, I have to add 1 to that number and pass that up. So as long as there's separation and clarity about how both of these can be solved, we can go ahead and write the code. Any questions about uh, conceptually what we have to do before we write this up? Okay, let's write this up. So as we did last week, we are going to uh, start out by writing the helper function, which is really the work that an arbitrary manager is doing. So an arbitrary manager is taking responsibility for a subtree, and so the root of their subtree would be this tree node called as node. Our tree node has the same structure as we had last time. It has an integer value, and it has two references for left and right to two other tree nodes. So this is our tree node structure. So node is an object of that tree node class. Node.val will be the integer value. Node.left would be a reference to the left child, and node.right would be the reference to the right child. Okay, so since this is post-order DFS, I'm going to start out by making the two recursive calls. And notice that I don't have any additional parameters here because the information is flowing bottom up. So I have to delegate work to my two subordinates, but um, that delegation is part of basic DFS. That doesn't really depend on whether it's pre-order, post-order, or in order. The work has to be assigned, but um, there's no additional information that I'm passing down because I'm not doing any work upfront. I'm waiting for them to do their work before I step in. So I'll make the two recursive calls first. Um, so I'll say if I have a left subtree, that means node.left is not null. If I have a left subtree, then I'm going to make a recursive call. Now I need to capture the return value from that recursive call. So I'm not going to make it like I did last time, helper node.left, because now I need a return value from it. So I need to store that return value. What is the return value? What am I expecting from my left subordinate? I'm expecting them to tell me what the height of their tree is. Right? So it's an integer return value. So let me create a variable left subtree height. Left subtree height is going to be the return value from my recursive call. And likewise, I hire a right subordinate if I have a right subtree. And the return value from that recursive call is something I'll store in an integer variable called the right subtree height. Okay, so after this, I'm going to have to do the work, post-order depth first search work. And that work has two parts, as I wrote down in the previous slide. I need to solve my local problem, but I also have an additional task of making sure that the relevant information that my manager is expecting from me is also created and passed up. That will be the final return value. So um, so which one of them should we solve first? We can start with the return value that I need to pass up to my manager. So whatever the height of my left subtree is, my left height is going to be one more than it. So I need to add a 1 to get my left height. Same thing for the right subtree. If the right subtree height is whatever it is, I'll add a 1 to get my right height. And then I'll pick the bigger of those two. So even though I can write this in a more compact way, just to be descriptive, since this is the first problem, I'll just make these two variables explicit, that my left height is one more than my left subtree height. My right height is one more than my right subtree height. And so my height right? My subtree height is going to be the bigger of these two values, max of my left height and right height. Now I could write this directly by saying, my subtree height is 1 plus the max of these two. Instead of three separate lines, I could just say 1 plus max of uh, left subtree height comma right subtree height. Um, so I'm just writing it in a more descriptive way since it's just easier to understand, but you can feel free to make it more compact. This is what I'm going to return. Okay, so I'm going to return up to my manager my subtree height. So that completes this particular task. This is the information I got from my two subordinates, and so I have to make sure I pass that same information up to my manager. But the reason I wanted the information from my two subordinates is to solve my local problem. What's my local problem? To determine if I'm height balanced. So I will be height balanced if my left height and my right height differ by no more than 1. If they do differ by more than 1, then I have a say in the final answer, as in I have to go out and set the answer to false in that global mailbox. If I find that the answer is true, I don't really have an influence on the global mailbox. Actually, if you think about what should that global mailbox be initialized to, because we are doing the AND of all the local answers, by default, the global answer should be initialized to true, so that when we do the AND operation, even if there's a single false, the final answer would be a false. Just like if we are doing addition, we start out by default with a value of 0, a sum of 0, and then we start accumulating the values being added. When we are doing multiplication, we start out with a default product of 1, and then we start multiplying each individual number. In a similar way, we are accumulating a bunch of the results of a bunch of AND operations. So by default, we should start out with whatever the uh, identity element is for AND, which is true. So I'm going to have a global mailbox which is going to be outside this red box. So I will initialize it outside. Let's call that external variable as, it's going to be a Boolean value. Let me actually indicate that it's so global answer is true. Now, if I find that my local answer is false, then I'll have to update the global answer. So what's my answer? Let me calculate my local answer. My local answer is going to be the difference between the left height and right height. And if that difference has an absolute value that's more than 1, then I'm going to tap into the global answer and set it to false. So if the absolute value of left height minus right height is more than 1, then I'm going to set that global answer to false. Otherwise, it remains true. It retains its original value. If my local answer is true, I don't have to do anything. But if my local answer happens to be false, I have to set it to false. Maybe it's already false, in which case this will be a no op. But if it is true, then this is going to change it to false. Okay, so that completes almost the entire code. But we do have to think about what will happen if either I'm a leaf node or maybe I'm a node, an internal node, but I have one of the two children missing. Right? I have a left subtree height coming back from the recursive call right subtree height. I add the two. I add one to both, and then I use it to compute my global answer. But what if my left child did not exist? So maybe I have a right subtree, but I don't have a left subtree. In which case, what do I want my left subtree height to be treated as? So we can, again have a separate piece of code for a leaf node if we wanted to, but to keep the code compact, we don't want to change any of this. We want this to work even if my left child was missing. So if my left child was missing, it's clear that my left height should be 0. Right? My left height should be 0. Now for my left height to be 0, 1 plus the height of my left subtree should be 0. So I should define the height of my left subtree to be -1 in that case. So and the same thing goes for my right subtree. So my left subtree height, something I'm going to initialize by default to -1, and my right subtree height is also something I'll initialize to -1. So if either of those two children are missing, my left height and right height will end up being 0. Or maybe both of them are missing, in which case both of them will end up being 0. So this code will run irrespective of whether it's a leaf node or an internal node with only one child or an internal node with both children. I focused on the most general case, an internal node with both children. That is what I wrote the code for, assuming that I have both children. And then I'm just coming back and saying, well, what if one of the two children don't exist, or maybe both of them don't exist? The code that I've written should still continue to work. So how do I ensure that it works? I ensure that it works by making sure that whatever answer, whatever final answer that I want from either side, either the left side or the right side, that final answer will be generated. And so I just go, reverse engineer what should the default values of these two variables be, so that those answers get generated in that event when at least one of the two children is missing. So that completes the code being executed by an arbitrary manager. And so The root manager is going to be executing the same code. The root manager executing this code is what will launch the entire boundary walk. So we just have to figure out with what parameter is the root manager going to execute this code. The root manager is going to be given the root node of the tree. So that will be the parameter with which they run the code. And once they've run the code, the entire boundary walk is going to be triggered. And along that boundary walk, wherever we are going up, right, wherever we are going up, that's where information is flowing up from each child to their parent. So the actual work of solving the problem will start being done by the leaf nodes at the bottom, and it will be completed once the root manager does their work. So this right protrusion from the root manager is indicating where exactly along the boundary walk are they going to finalize their answer, and that's going to be at the very end. The very end of the boundary walk, which by default goes in a left to right order. But these downward uh, movements are the delegation calls, right? This is where each manager hires a subordinate to ask them to do that work, right? So the recursive calls have to be done. These two recursive calls have to be done to do the boundary walk, irrespective of what kind of DFS it is. Right? So this is what is going to trigger the boundary walk. And once this function call returns, that means everyone's done their work. And so we can return the global answer. And as before, we'll have an extra line, just like we've had in the first two classes. If the tree is empty, then we want to return our special answer. In this case, uh, we are asked to return a true. So that completes our code. Depending on which language you're using, you can write this helper function code as an inner function within the outer function, which actually solves the overall problem, or you could move this out as a separate function. That's a language specific thing. I'm just writing it within the outer function code here as an inner function. Feel free to do it the other way if that's what your language requires. The time complexity of this is going to again be determined by the time complexity of this red piece of code, because everything outside here is it's constant time. The boundary walk itself, as you remember from last time, is going to need linear time, but the additional work being done at each node might add to it. But if you look at each line here takes a constant amount of time to run. And so overall, this entire red piece of code runs in constant time, theta of 1 time. So if each manager is doing a constant amount of work, then collectively the entire hierarchy is doing work that is linear time, linear in the size of the input or the number of nodes in the tree. The auxiliary space used is really the space on the call stack, because we are making recursive calls here. So we are building up as we go down the tree along the boundary walk. We are adding more and more activation records to the call stack, like we saw last week. So the space on the call stack, in the worst case, would be the maximum height of the given tree, which could be theta of n, because the tree can be highly skewed. In the worst case, it could be a chain like this. So this is going to be theta of n, right? Each manager is only adding um, a few local variables, constant number of local variables. So the space within each activation record on the call stack is going to be constant. The entire call stack might have a space, a total space that is proportional to the number of nodes in the tree. Because the number of nodes along the longest path from the root to any leaf could be n, or some fraction of n. So that completes our first problem. Are there any questions on this? Okay. Quick question. So the child nodes to the parent node should pass two things: height of the tree and if the subtrees are height balanced. So you can implement this code by returning not just what the manager needs, but your local answer as well, right? So instead of the local answer tapping into a global mailbox that's lying outside, like a global variable for all employees to access, you could pass up your local answer along with this piece of information. You can implement it that way too. I don't do it that way because it it obfuscates the difference between these two conceptually. This piece of information is something that is required to solve the local problem for each manager. It is not it's not a local answer, it's not a global answer, right? This information has nothing to do with the actual answer to the problem. The actual answer to the problem is given by this. And that actual answer is something that can lie in a global mailbox outside. It doesn't have to be something passed up or constructed by, uh, necessarily passing up the local answers. The way I write the code is the information that is passed up is critical information that is needed to solve the problem. The local answer does not have to be passed up. It can just straight away tap into the global answer. Okay, so hope that clarifies the difference. You can uh, not have a global mailbox outside and instead just pass up the local answers. Everyone's passing up along with the height, the local answer to the problem. So the manager would then have to do the work that's happening in the mailbox, right? Taking the and of both the local answers returned on both sides, uh, and then continue to pass up that local answer. And so the global answer then would be constructed by the root manager when they take the and of the local answers on both sides. So that's another way to write this. I don't, Yeah, I won't. I'll follow this particular style which I've done here. Can you please explain how that code you just initialized to -1 does not get called during a recursive call? Uh, so if I don't write this, and if I just execute this, what's going to happen is that I'm going to get an error because these variables are not defined, unless both these children exist, right? If I have an empty subtree either on this side or on that side, at least one of these two variables are not going to be defined because uh, there was nothing passed, there's no information coming from below, right? So when there's no information coming from below, what should I assume the left subtree height and the right subtree height to be? So your common sense may say, well, shouldn't it be 0? Well, maybe, but if you want to reuse the same code, we want to make sure that, so we know that at the leaf level, everything's balanced. Any leaf node has no left child, no right child. So the answer has to be um, that it's balanced. But this is not just about leaf nodes. It's also about internal nodes which have a missing child, right? So they are going to compare their left height, which means the number of nodes along this path, starting from themselves down to any leaf in the right subtree. Uh, they're going to compare their their right height with the left height. The left height, um, you could argue, should be um, so it depends on how you define the left height. If you are including this vertex also, then you would define it in one way. If you are defining the height in terms of the number of edges, then there might be a slight difference uh, in the way to look at this. Let me look at the next problem because that also uses the same information. Um, yeah, so the convention in these problems is to use the number of edges. And so what we want is we want the number of edges down each side to define the height, right? There are two slightly different ways of defining the height of a subtree. One is you look at the longest path from the root down to any leaf and focus on the number of vertices in that path. A slightly different way is to focus on the number of edges along that path. So if you focus on the number of edges along that path, that number is going to be one less than the number of vertices along that path. Okay, so whatever you adopt, you just have to be consistent. So let's say we are talking about the number of edges along the path as defining the height. So if I get the height of my right subtree, which is the number of edges along the longest path inside this subtree, then I'm adding 1 here to get my right height because I have an extra edge here. If I don't have a left subtree, then there are no edges on the left side to talk about or to count. And so my left height should be 0, right? I want this um, to be 0. So if I want this to be 0, this needs to be -1. And that's why I'm defining this to be -1. So this is going to be the value that will come in that will be used for computing the left height if there is no left subtree, right? So inside this recursive call, I'm not passing the left subtree height there. So, it's going to be something that's coming back from my left subordinate. Right? So then that value will get stored there if it exists. If it doesn't exist, this is the value that will get used here. Does that clarify that answer, Mohan? Do we need to keep recursing once the global answer is false? Um, no, we don't need to keep recursing if the global answer is false. So, but this is a decision problem, and for some problems you can short circuit out, but I don't want to do that here because it'll make the code for these exceptional kind of problems to be different, and that just when you have different ways of writing the code for different problems, then the chances of making an error increases. So I just want to stick to this because when um, in other problems, um, we will need to uh, we'll need to we cannot short circuit in general. This is only in the case of decision problems that we can do it. So to have just one template, I'll keep it this way. If node is none, return 0. Can simplify those lines. Yeah, so another way to do this would be to handle uh, no, sorry, Shankar, node is none. Node cannot be none. We we are assuming that every manager is taking responsibility for an actual subtree in the tree. So node itself cannot be null. Right? We don't make this recursive call if um, our left or right subtree does not exist. For some of these problems, you may find that yeah, well, uh, if we allowed node to be null, the code would be shorter. That might be true for a few problems, but again, for other problems that won't be true. And so once again, just to stick to one particular template which works for all problems. Um, I'm not like trying to do anything ad hoc for this specific problem. Yeah, not short circuiting out is not going to change the asymptotic complexity, right? Because in the worst case, if the tree is balanced, we know that we would have to parse the whole tree in order to figure out that it's balanced, right? The root level, the root manager um, is the one who has the final answer. If you look at this toy example, the tree was balanced at every level except at the root. It was at the root that the first and the only instance of imbalance happened. And that was detected only at the very end when the root manager integrates these two pieces of information. So if the tree was balanced or if it was imbalanced at the root, we see that we cannot short circuit our way out. And so the worst case complexity is going to remain theta of n, even if you short circuit out, because that short circuiting out will not work for these kinds of examples. It's not going to help you. Question here, if we are calculating the height at the root level um, and the subtree level, it may O of n by 2. I'm wondering about the total time complexity. It should be more than O of n. No, so the height at the root level is not taking O of n. The height at the root level is um, is being computed in constant time because it is using the height information from the two subtrees. Right? This information is passed up from both children. So we are not, adding, we're not doing O of n work here. Every manager is adding that one to the heights of their, two subtrees. So collectively, it's going to take or big O of n. As long as this red piece of code takes constant time, the overall time is guaranteed to be theta of n. And when I say this takes constant time, I'm just counting here the time for making the function call and returning from the function call. The actual time for executing these two is going to be accounted for within the red boxes of those two subordinates. Right? So think of the time complexity of this as just the complexity of making the function call and returning from the function call, not in actually executing this on node.left, because for that we would go down to that we would do the accounting by looking at how much time my left subordinate would take to execute this piece of code. How about the approach of keeping level as global and return false when the height balancing condition is not met? All decision problems, the global variable should be Boolean and not the result of the work done. Yeah, for decision problems, in general, you can bail out earlier. Um, Level as global. No, sorry. You'll have to then maintain multiple pieces of information because the imbalance can happen at any node. So, um, I'm not sure what you mean by level. Yeah, I'll just unmute you. Yeah, go ahead.
Okay, can you hear me?
Yeah, I can hear you.
Okay. So what I thought first when I looked at the problem is if I maintain level as in the height as a global variable, and then I can update the height when I am actually doing the work. And if the condition doesn't meet, I return false there itself. Uh, is
Which
that
which height are you maintaining? When you say height, which height? Height of what?
height of the tree? Like I start from the root, I start with, past the root node, and level is set as 1, and then the helper function accesses that global level variable to calculate, like add 1 to that level, and calculate the left height and right height. And if it doesn't match, or if it doesn't meet the condition, if it's greater than 1, then I return false directly, else I return the level, which means that I see, will it be because
So the level is, it's a different number for each node.
yeah.
So when you need two different levels to compute your level, so I'm
Mm.
still not clear
Okay.
to me how you're going to integrate the answers from both sides if all you're maintaining is one global level.
I see what you're saying. Okay.
Yeah, whereas we know that the global answer here is the AND of all the local answers, and this is something that can be built up in an incremental way, right? If we have the old answer and we get a new local answer, just take the and of the old answer with the new local answer, and that updates your cumulative answer.
Okay. So then for decision problems, as you said, there are two tasks, right? One is to return something, and one is a boolean. So then it's easier for us to kind of keep that framework in mind that we can return directly, we can keep the boolean as a global variable, and whatever work we are doing, we just process it in the helper
Yeah.
function,
So
right?
this is, yeah, this is not something specific to decision problems. This is going to be true for every single problem we see today, which is why I'm
Okay,
giving this. Talking about this framework, and I'm avoiding doing things micro optimizations which apply only to to decision problems with Boolean answers. This first problem is a decision problem, but these two subtasks, breaking up the work of each node into these two subtasks, is going to be there even for counting problems, optimization problems, as you'll see with the next set of problems we take up.
great. Yeah. So what I was confused about is that, is there a thing that we can keep in mind, what should be a global variable, what should be a local variable? uh, is there anything that you can suggest for that? Because here there are multiple things we need to do, right?
Yeah, the whatever the global question is, the
Mm-hmm.
answer to that is going to be in the global variable. The question
Okay.
here was determine if it is height balanced, right? Is the whole tree height balanced? So it's that's the global problem. And so the answer to this has to be kept in a global variable.
Okay.
The local
Okay.
problem is going to um, be a local answer, and some operation done on all the local answers is going to be your global answer. So the answer to this global problem is going to be a formula which combines all the local answers using some operation. It could be and, it could be or, it could be sum, it could be product, it could be max, it could be min. Whatever that operation is, the answer can be built up in a cumulative way, which is what allows us to write the code in a way that we are pretending we are tapping into that global mailbox and updating that cumulative global answer.
Okay. Yeah, that
Yeah.
helps. Thank you.
This is always going to be the return value. This is going to be where we update the global answer, right, in a cumulative way.
Yeah.
Okay, any other questions? So, yeah, so please keep in mind that here the definition of the height we are using is based on the number of edges along the path, not the number of vertices. Otherwise, if we had vertices, then for an empty left subtree here, we would still count this, right? There are no vertices here, so that answer would be 0, but then this answer would need to be 1, right? So as long as you follow the same convention on both sides, you might get, slightly different initial values here, but as long as you're consistent, things will work out. Okay, because everything in the tree will have a number that is one less or one more, depending on whether you define the height uh, based on number of nodes or number of edges. So as long as you're consistent everywhere, it's the height difference that matters. So it's not going to make a difference whether those two numbers that you're subtracting here, um, if you have, you know, 5 minus 4 or 4 minus 3, the, the difference is still going to be the same. Okay, in case this minus 1 was confusing, I mentioned this. Okay, so as we see more problems, you'll see that a lot of what we are doing here is common to all problems. And so hopefully the learnings will get consolidated. The next problem that we want to take up is the problem of computing the diameter of a binary tree. You are given a binary tree. This time we want to return the length of the diameter. What is the diameter of a tree? It's the length of the longest path between any two nodes in the tree. Now, this path may or may not pass through the root. And you have to pretend that the length of the path is uh, the number of edges along that path, not the number of vertices. So, in this toy example, look at all the different paths that are there in the tree. This is one particular path. It has three edges. This is another path that also has three edges. This is another path that has two edges. Even this is a path. It has one edge. So think about the longest path. So when you're trying to figure out what the longest path is, you don't want to stop the path at an intermediate node, right? You want to continue as long as you can. So you'll start at a leaf node and you're going to end at a leaf node. And so you have this as an option, you have this as an option, and you have this as an option. And you can see that this path as well as this path, both of them have three edges along them. And so that's the diameter of the tree. There is no path that is longer than three edges in this tree. In the second example, when your tree looks like this, there is only one path and that will have a single edge. So the diameter is going to be 1. The number of nodes in the tree is going to be at least 1 here. So, which basically means that when we finish writing our code, we don't need uh, that empty edge case that we had here. But that's a minor thing. The question is, how do we solve this problem? I saw somebody raise their hand. Way above. For the diameter of a tree, does a path need to start from a leaf node and end at leaf node? Okay, so that hopefully got answered. Um, um, Suppose, and you can argue that even by using a simple proof by contradiction, right? Suppose there is a path which does not end at a leaf node. Can that path be the diameter? Well, if it's not ending at a leaf node, then you could make it longer, right? Extend it, because that means there are edges in front of you that you have not included in the path. So you can make that path longer. And so, which means it was never the longest path to begin with. So that means the diameter must start at a leaf node and must end at a leaf node. Okay, so what does the diameter in general, what is it in general going to look like? If my tree is, let's say, having this kind of shape, the diameter is going to start from a leaf node and end at a leaf node. So it's going to go up like this. Oops. It's going to go up like this, and then it's going to, maybe come down like this to another leaf node. Right? That's going to be the general shape of the diameter. It's not necessary that it has to look like this inverted V, because who knows, there may not, this may not exist or that may not exist. The tree might be highly skewed. But that's the general shape. So we can say the diameter the diameter path will be inverted V-shaped in general. Why is this important to note? Because that means in order to compute the diameter, we can't just rely on information that is flowing purely downwards from the top. Because this information, the length of this part of the path and the length of this part of the path, they are lying on two separate branches. They have to be added together, right? That will be the length of the diameter. And that cannot be done in a top-down way. Anytime you need information from the left subtree and from the right subtree to be integrated together, you would not go in the direction of using pre-order or top-down DFS. You would want to think about bottom-up DFS so that you have information from both sides which can be integrated together. In this case, added together. So anyway, let's start thinking about this problem. The global problem here is to find the diameter of the whole tree, which is going to be an integer, not a Boolean value this time. So what can I as a lazy manager do? How does my node, assuming my node looks like this, I take responsibility for the root and I have two subtrees. Well, if the diameter path does not pass through me, then I don't have any contribution to make. But of course, how do I know whether or not the diameter is going to pass through me? What can I do at my level or at my node? So let's call this node as the cusp of the path. Right? The diameter, the path which makes up the diameter, it rises up and then it comes down. So if I can compute what is the diameter of the tree, assuming that it's constrained to pass through me, and if everyone in the tree does that, then we can all compare our respective diameters and figure out what's the overall diameter of the tree. Right? So either the diameter passes through me or it doesn't. So the only thing that I can do to solve the problem is calculate at my local level what would be the diameter if it passed through me. So the local problem, right? Find the diameter assuming the path is passing through me. That means assuming the cusp of that path is at my node. So if everyone in the tree does this, then we would be comparing every possible, V-shaped path, inverted V-shaped path. And whichever node actually lies at the cusp, their local answer is going to be the best answer. What does best mean in this case? The diameter of the binary tree is the length of the longest path between any two nodes in the tree. So in that sense, this is really an optimization problem. It's important to note that this is an optimization problem. We're trying to find the length of the longest path. We're trying to maximize the length of any path in the tree. So the maximization problem. So the global answer, how do we get the global answer from all these local answers? We have to take the max of all the local answers. An answer is better than another answer if it's bigger than the other answer. So if every manager or every node is able to calculate what is the diameter, uh, assuming that it's passing through it, that would be the local answer. And by computing that local answer, we could again pretend the global answer is in a mailbox lying outside the office. We just peer into it. If we find that our local answer is better, which means higher than the existing answer, we just overwrite it. So how do we compute our local answer? Right? That's what our the crux of the problem is. How do we find the diameter assuming that path is passing through me? So what information am I going to need from my two subtrees or the two subordinates to compute the local answer? If this path, oops, if this if this path is the longest, then one thing that is clear to me just from the observation that is the longest path is that within my, let's say, left subtree or within my right subtree, this green path that I see should be the longest path. Well, should be the longest root to leaf path in that subtree. Right? This path should be the longest root to leaf path in the subtree, because if it wasn't, if there was another longer root to leaf path within my left subtree, then I could take that path and add all these edges and get a better answer, a bigger diameter. That's a contradiction. If this green path is already the diameter, there should be no way to improve it, which means within the left and right subtrees, that path includes the longest root to leaf paths within those subtrees. So that is the information I would want from my left and right subordinates. What is the longest root to leaf path within your subtrees? If I could have that information, then I could add one more edge on the left side. I could add one more edge to the path on the right side, and I could get the diameter through me. So that would be my local answer. So what did I write here in the first problem? I wrote, I need to pass. So once again, notice that the information I actually need from my two subordinates is the longest root to leaf path inside your subtree. What is the longest root to leaf path called? Well, it is the height. Right? That is by definition the height of the subtree. So even in the second problem, I need the same information. I need the height from my subordinate. And if I need the height from my subordinate, I have to pass that same information up to my manager, because my manager is also going to need the same information from me. What is my height, my subtree height? I also need to solve my local problem. That's actually my main task. But I realized that if I was expecting some information from my subordinates to complete my task, I also need to uh, do the same work for my manager. Otherwise, I'm not going to get that information from my subordinates, since everyone executes the same piece of code. Okay, so again, I'll focus on doing this first, and then more patching onto it the other, or the main goal that I have, which is to solve my local problem by using that information. So I need from my subordinates the information as to what is the height of uh, both the subtrees. We do that on the next page. So I'll write the helper function code first. In bottom-up or post-order DFS, there is no information coming from above. So when we are given the subproblem to solve, we assume that we are only given the root node of the subtree. That's it. And the first thing we are going to do is to make those two recursive calls, which are going to give us back our left subtree height and our right subtree height. All right. So let me write it again. It's really the same thing. If I have a left child, if I have a left subtree, then I'm going to hire a left subordinate and ask them to return to me the height of their subtree. Same thing if I have the right subtree. Having got that information from both sides, I can now think of what work am I going to do. I have two things to do. The first is to make sure the same information is passed up to my manager. That's going to be the return value of my function. Right. So in a sense, the return value of my function is something that has nothing to do with what the problem asked. The problem did not ask me to compute the height of my subtree, but the information that I'm returning back is the height of my subtree. So it's not a distraction, because that is the information I needed from my subordinate to actually solve the problem. So that will be the return value. So how do I get that? Well, in the same way, if I have, assuming both of these subtrees exist, if I get the left subtree height here, I'm going to add 1 to get my left height. I'll add 1 to my right subtree height to get my right height. And then my subtree height is going to be the max of those. Uh, right. So So my left height is going to be 1 plus my left subtree height. Again, I'm being verbose here just to be clear what each number means. My right height will be 1 plus my right subtree height. And my subtree height will be the uh, max of these two. Left height and right height. And this is what I'm going to return. So I'm going to return my subtree height to my manager. But this is the less important. I mean, this is, I shouldn't say less important. This is critical for solving the problem, but this is not the main problem. The main problem I have to solve is my local problem. What's the diameter, assuming the path passes through me? So I have to take my left subtree height, my right subtree height, and add 1, both of them. That'll be the answer to my local problem. Okay, or equivalently, I can just add the left height and right height. That'll be the uh, answer to my local problem. So I'll tap into that global mailbox. So let me uh, call that the global diameter. So what should it be initialized to? So it's the max of all the local answers. And so what is when we are trying to find the max, what is the default value we should start with? We should start with a value that's impossible, uh, to see in the tree. Should be so low that we're not going to see that in the tree. So it could be a negative value, it could be 0, and then every local answer potentially increases it. Right? If I set it to plus infinity, that would be a huge mistake, because then it's going to stay at that value. We want, even if there's a single edge, it's possible that the final answer could be one edge. It's also possible that there may not be any edge, right? If there's an isolated node in the tree, making up the whole tree, then there's going to be no path in that tree. So then the answer would be 0. So 0 seems to be the smallest possible value that the diameter could have. So let me set it to that. I could set it to something negative, but as long as it's the smallest possible value, that's good enough. So what I will do is I will update it. So my local answer is left height plus right height, right? The sum of these two, or the sum of these two. So if if that value, let me write it like this: if my left height plus right height is bigger than the value stored currently in the global mailbox, then I'm going to update the value stored in the global mailbox. Okay, so that is what I'm doing here in the general case where both children exist. But what if both children don't exist? What if I'm a leaf node or I'm an internal node where one of the two children is missing? What do I want my left height and right height to be in that case? Clearly the left height, so if I don't have this part at all, then my left height should actually be 0. Right? Likewise, if I don't have a right child at all, then the contribution of this entire thing should be 0. So this is 1 plus this right subtree height. This is 1 plus the left subtree height. So if there is no left or right subtree, then I want these two values to end up being 0. That means 1 plus these should be 0, which means these should be initialized to -1, so that I don't have to analyze these cases separately. If I'm a leaf node, if I'm an internal node with one child, or an internal node with two children, in all three cases the code will work as long as I have the right initialization for what the answer should be from the left side or the right side, uh, or what the information passed up should be from the left side and right side, if those subtrees don't exist. So my left subtree height is something I will artificially set to -1. Because otherwise these variables will not be initialized, and I'll be using them, and that'll give me a syntax error. Right? So whatever return value I am getting from my subordinates, I have to find a way to initialize it to the appropriate value so that if they don't exist, if those subtrees don't exist, I still, the code that uses that information to compute the local answer is not, and to compute the answer that will be passed up to my manager, that code won't break. So once again, this is the code that I run and which everyone runs in the corporate hierarchy. It is run by the root manager with the root node of the tree as the parameter. This is what initiates the boundary walk, and you know this is what triggers the boundary walk, and at the end of the boundary walk the answer would be lying in the global mailbox, so we just return that. The complexity is going to be the same as in the previous problem, because we notice that every line here takes constant time to run. And once again, for these two lines, we are accounting for the time needed for making the function call. We're just delegating that work. You can even say the time needed to return from it is not required, because if we are accounting for this, for this line, the final line here, into our cost, then the the cost of returning from these two functions will already have been accounted for within the last return statement of those two function calls. So it's just the cost of delegating, strictly speaking, that is going to be the cost of these two lines. So since everyone takes constant time to run their piece of code, total time complexity will be the sum of all those times which is going to be theta of n, assuming there are n nodes in the binary tree. The call stack space, once again, will just be, in the worst case, theta of n. That's the total space used in the activation record for all the local variables of all the currently active function calls. And in the worst case, that will be uh, equal to the height of the tree, which in the worst case could be theta of n. I didn't get why we're returning the subtree height. I thought it would be the global diameter. So within the function call, what we need to return is what we were expecting our subordinates to give us. Because if we are returning our local answer, then our subordinates are going to return their local answer, which is irrelevant for me to solve my local problem. For me to solve my local problem, the information I need from my subordinate is what is your subtree height. So my manager is going to expect the same thing from me. So my focus should be on returning my subtree height. Right? I can't get one piece of information from my subordinate and pass up to my manager something different from that. Then this whole process is going to break. So it's important, therefore, to separate out these two tasks. I first do this, so I get the return, whatever information is to be returned from the function. But I also then do this, which was my original goal. But I have to insert the code for this somewhere in the middle. That's not the focus of what I'm returning to my manager. Any other questions on this? No? Okay. So the first problem was a decision problem. The second problem was an optimization problem. The third problem that we're going to look at is a counting problem. So you're given a binary tree, and we need to count the number of subtrees in it which have just a single value inside the nodes of that subtree. That's called a uni-value subtree. Right? So a uni-value subtree is a subtree in which all the nodes have the same value. So in this first example, the tree seems to have multiple values, right? You see a 1 here and a 5. So the tree as a whole is not uni-value. But if we look at subtrees, different subtrees inside the tree, so this is a subtree that is independently uni-value. This is a uni-value subtree. This is a uni-value subtree. This is a uni-value subtree because it has only 5 in it. But this is not a uni-value subtree because we see two different values, 1 and 5 in it. So if this is not a uni-value subtree, any subtree that contains it is not going to be uni-value. So the overall tree is not uni-value. So, but how many uni-value subtrees did we count inside that overall tree? Well, this was 1, this was 2, this was 3, and this was 4. There were 4 uni-value subtrees. If the tree was empty, it had no information, then the number of uni-value subtrees in it would be 0. There are no subtrees in it at all. Forget about uni-value. So the uni-value subtrees would also be 0 in number. In example 3, let's see, the tree it has 5, then it has both children as 5. This has both children 5. This has a right child called 5. So how many uni-value subtrees are there? In fact, there's only one value in the entire tree. So every single subtree is going to be uni-value. So that's 3, this is 4, this is 5, and the whole thing is 6. So there are 6 uni-value subtrees. Actually, in general, how many subtrees are there? The number of subtrees in a tree with n nodes is going to be how much? Here we had 6 nodes and there were 6 subtrees. Is that a coincidence, or will it always be true that the number of subtrees in a tree with n nodes is going to be n? Is that true? So each tree will always be counted as a uni-value subtree. That's true. So each subtree is rooted at some node, right? When we distinguish one subtree from another, their roots are obviously different, right? If the roots are the same, then the subtrees are going to be the same. You have to go all the way down. You have to collect all the nodes in that subtree. So the number of subtrees in a tree with n nodes is just going to be the number of nodes in the tree. So because every node defines a unique subtree under it. Some of them may be uni-value, some of them may not be. But in general, the number of subtrees in a tree with n nodes is going to be always n. So how do we tackle this problem of counting the number of uni-value subtrees? So once again, we have to think of ourselves as lazy managers, and we are asked to compute the number of uni-value subtrees in the overall tree. But what is the bare minimum work we can do involving our node and potentially the 2 subtrees, but just our node to figure out our contribution to the answer? So as a root manager of the overall tree or of the subtree rooted at me, I can take responsibility for the subtree rooted at me. That's it. So if I can figure out whether the subtree rooted at me is univalue or not, then my contribution to the answer will either be a 0 or a 1, depending on whether my subtree is univalue or not. And if everyone does that, then their local answer will be either a 0 or a 1. Collectively, all of us would have figured out the global answer, which would be just the sum of all the local answers. So we can say the global problem is to count the number of unival subtrees. The local problem, or the work that I am thinking of doing, is figuring out whether the subtree rooted at me is unival or not. If the answer is yes, then my contribution to the global answer is 1. If it's no, then it's 0. And so the global answer is going to be the sum of all the local answers. So how do we know at this point whether we are doing post-order DFS or not? If we are to figure out whether the subtree rooted at us is unival or not, is that something we can figure out if the information was flowing top down? No, if the information was flowing top down, we would not even look at our subtrees. We would have no information about our subtrees if information was purely flowing in a top down fashion. And the leaf level workers, they would not know if, well, firstly, they would be part of different subtrees, and they won't know if the other paths in the subtree have a different value, um, even if the path leading up to the root is unival. So the focus here is not on an individual path going up from a leaf towards the root. That was the focus last week when we had those top-down problems. The path sum problems, for example, had paths that went down. Well, even if they didn't start from the root, we saw there was a complicated problem which didn't require things to start from the root or end at a leaf, but they were still purely ancestor descendant paths. We never had a path spanning, or an inverted V-shaped path, and we never thought about entire subtrees. Right, an inverted V path is like that, which we looked at in the diameter. A subtree would be not just an inverted V path, but it would also focus on all the nodes in the middle. So in either case, whether it's an inverted V path or whether it's the entire subtree, if we need information about the entire subtree or an inverted V path, that information can only come in a bottom-up fashion. It cannot be built up in a top-down way. So what information would I need from my subordinates to figure out if I'm unival or not? Assuming I cannot um, peek at anything outside of this, uh, outside of my value, and at most I can cross these two bridges, but I cannot peep inside these subtrees. What information do I need from my subordinates here? So without looking at all of these values, um, what summary information can come from both sides that tells me or helps me decide if I'm unival or not? Yeah, so my left and right subordinates have to tell me whether these subtrees individually are unival or not. So what I need from my left child is um, the left subtree unival? That's the question I'm going to ask from my left subordinate. Here, take the left subtree, figure out whether it's unival or not. For my right subordinate, I'll do the same thing. If a right subtree exists, is it unival or not? That's the information I need for my two subordinates. If either of them says no, then I know. So let me write this down in English. If either of them say no, then it means I'm not unival. Right? But what if both of them say yes? If both of them say yes, then what? Does that mean I'm unival? Well, not necessarily, because what if the left subtree is filled with ones and the right subtree is filled with fives? Or what if both subtrees are filled only with ones, but the value at my node is a 5? So what I need them to tell me is not just whether they are unival or not. I also need them to pass to me that number, which is that single value. And my value happens to match, the single value from my left side, um, which will obviously be equal to the value um at the root of the left subtree, or I can just expect them to pass me that as part of the return value. And it also needs to be equal to the value on the right side. Then I know I am unival. Otherwise, I'm not. So I wrote the English logic here. And so I can proceed and write the code this up using the same template. But remember, we are supposed to do two things. One is figure out our local answer. That is what I've written this code for. But if we are expecting them to tell me if they are unival or not, I should be passing that same information up. But it turns out that in this particular problem, it's convenient that my local answer is also the answer that I need to pass up. If I am unival, then I pass up to my manager a boolean yes. Right? So I don't have to do any extra work to figure out what I need to pass up. In fact, when writing the code, we'll do what we did in the first two problems. First, figure out what it is that I need to pass up to my manager. I need to figure out if my subtree is unival or not. So uh, this is what I'm going to pass up as a boolean flag. But if I know whether I'm unival or not, then I also know my local answer. So I'll also tap into the global mailbox and add a 1 if the answer is yes. So let's write this up using the same template. Um, so we'll have a function that is being executed by everyone in the corporate hierarchy. And the very first thing we'll do is to make those recursive calls, those two recursive calls, and uh, store the answers to them in two Boolean variables. So if the left subtree exists, then I'm going to store the answer to the question, is the left subtree unival, in a Boolean variable. Let me just call it left subtree unival. Similarly, if the right subtree exists, then I'll ask my right subordinate to return to me the answer to the question, is the right subtree unival? So these are both Boolean variables. Then I have to do the post-order depth first search work of figuring out both what value I need to return to my manager and also the answer to my local problem. So let's do them again in that same order. I want to figure out if my subtree is unival. Right? Am I unival or not? That's going to depend on what these two Boolean values are and whether um, my value matches those two values. So assuming both of them exist, what would I say? I would say if my left subtree is unival and my right subtree is unival, and my value is the same as the value in at the root of my left subtree and the value at the root of my right subtree, then I'm unival. Now, there are two ways of implementing this, almost the same, really. It's really a question of how you're conceptually thinking about it. What I assumed is that the only information that's passed up by my subordinates is this Boolean flag. Are they unival or not? They could also pass to me a second piece of information, which is what is that unival number if they are unival, right? So, um, in fact, they could always just blindly pass to me the number at the root, right, or at their very inside their very node, because if they are not unival, it's not going to matter what that number is. If they are unival, I'll know what that number is by looking at that second field which they are returning. So I think I did write the code uh, in this particular way, but um, um, I'm just thinking if I should proceed in that other direction. Yeah, let me do that. So I'm going to assume that I pass not just that Boolean flag, but also the left uh, val, right? I get both of these from these recursive calls. And I'm going to get the right value from these recursive calls. So I might have to put them in a pair. Okay, you can say, well, why can't I just peer down? I can. That's also an equivalent way. In fact, that's what I have in the code here. But let me try doing this in a slightly different way as well, so that you get you have flavor of both. Because conceptually, I don't want to look down into the left or right subtree, right? I could do that, I know here, but I'm trying to just keep it clean. So I expect them to tell me what it is. So if the left subtree unival is unival, the right subtree is unival, and my value is equal to uh, the left value, which is in turn equal to the right value, then I know I am unival. So I'll have a Boolean flag saying I am unival is true. Otherwise, I am unival is false. And this is what I'm returning to my manager. Actually, in this modified code, I have to return both this value and if I'm unival, what is that unival value going to be? That's just going to be the value in my node. I'm returning this even if this is false. My manager is not even going to bother about this. Okay, so this is what I'm doing to satisfy my manager, but then I also have to tap into that global mailbox to update the global answer with my local answer. How do I do that? Well, if I'm unival, then I know I have a 1 to contribute there. Otherwise, I have a 0 to contribute there. So contributing a 0 is equivalent to not touching the global mailbox. I can just leave it as it is. But if I'm unival, right, if I know that I'm unival, Then I also have to add a 1 to that global answer. So assuming I have a global count, which is, because it's an addition, so you start out with a count of 0, I can add a 1 to that global count if I know I'm unival. The other thing I have to think about now is, what if one or more of these children did not exist? Right? I'm assuming both subtrees exist. This code should run even if one of them did not exist, or maybe both of them did not exist. So let's say the left subtree did not exist. Then, what answer do I want? Um, we have to think about what should these two values be initialized to so that they don't screw up the answer, so that they're consistent with the answer. If the left subtree does not exist, then it should not affect my calculation of whether I'm unival or not. So what should be the default value of this variable so that it does not affect whether I'm unival or not? Right? Only the right subtree will affect. And in fact, if both of them don't exist, then I know I'm unival, because then I'm a leaf node. So if both of them don't exist, then this entire thing should evaluate to true. So it's clear that when I have the AND of a bunch of expressions which I want to be true, by default I need to initialize both of them to true. Yeah. So I need to initialize both of them to true. So I'll do that here. Left subtree unival is true. Right subtree unival is true. Okay. What about the other two? These also I'm assuming I'm getting from my subordinates. They won't exist, right, if either of those subtrees don't exist. But I still want this to be true. I still want this to be to end up being true in that case. So yeah, so I need to set left val and right val by default to be node dot val. So I'm going to run as before this same piece of code in the red box with the root as the parameter if I'm the manager, and that will trigger the entire boundary walk, at the end of which the answer should be in the global mailbox. So I return the count inside it. Let's see, is there a possibility that the tree could be empty? Yeah, in this problem, you can have an empty tree. So I'll add that green line saying if the root is null, then return count of 0. The time and space complexity are going to be the same as before, because all of these lines If you just go through them one by one, they are all constant time operations. Again, these two lines are about just making the function call here, right? Don't count the time needed to actually run the body of the helper function for both of those. Those will be in the accounting of the managers who are responsible for those two subtree, those two subtrees. So the time and space will continue to be as before. Space here is on the call stack. Any questions on this? The code I have actually on the slides is slightly different. It assumes that the only information being returned is this Boolean value, right? Not the Boolean value with the value if it's unival. So just verify that this runs. Uh, if you're not returning that value, then you'll have to peer down into the left and right subtrees, but you have to again account for the fact that they may not exist. So if they exist, right, either they don't exist, or if they exist, then the value should be it should match. That's how I've written it here. But I just realized when teaching this that uh, you can do it without looking into the left or right subtrees. Both are basically the same, but I think this is conceptually uh, maybe a little more satisfying. What if current node is null? Left val and right val will be null. Uh, I mean, for assigning the left val and right val at the start of helper. No, current node can't be null. This cannot be null. That is why, I mean, in every single case, whether it's top-down DFS or bottom-up DFS, we are assuming that a manager is given a non-empty subproblem to solve. Right? There is at least um, at least the node, the subtree that they are given is non-empty. So there'll at least be a root of that subtree. This is necessarily non-empty, non-null. If the root is null, then we are handling that separately anyway. The entire tree is null. And if there is no left child, then we don't call the helper function, right? We call the helper function only if, fill this in, null. We call the helper function only if we know that the right child and the left child exist. And that's true for all problems. Again, there's nothing unique that I'm doing in this problem. It's true in all the problems. Not just for bottom-up DFS, but even for top-down DFS. Okay, so that, yeah, Vaibhav.
So, can you hear me?
Yeah.
So, my question is, let's say there are different leaf nodes. There are leaf nodes, and they each leaf node has a different value. Let's say one has 1, another has 2. Will they still be counted as uni-value subtree or no?
Yeah. So if, for example, let's take this tree. 1, 2, 3, 4, and 5. So these two subtrees are going to be counted as unival. 4, and 5. And even this leaf here at 3. But the other two this one and this one will not be counted as unival. So the answer for
Okay.
this in this case is going to be 3.
Okay. Thank you.
Anything else? Okay, so let's take a 30-minute break now and resume around 1:10 Pacific time. And then we can continue with more problems. Going back to the agenda. So we have 5 more problems to do. So we'll do it after the break. Okay, so let's begin with the next problem. In this problem, you're given a binary tree and you're asked to return the length of the longest path, which is unival. And the important thing here is that the path may or may not pass through the root of the tree. The length of the path is again represented by counting the number of edges, not vertices, but edges on that path. So in this first toy example, you can see that if you had to find the longest unival path, this path with 2 edges has only 5s along it. So that would be the longest unival path. It has 2 edges on it, so the output is a 2. In this second example, uh, there is a unival path here with 2 edges, and that's the longest unival path, so the output is a 2. Notice that here the path did start from the root and go down to a leaf, but it's not necessary. This path does not go through the root. In fact, it doesn't even have to start or end at a leaf, because you can imagine, suppose there was a 6 here and a 6 here. The answer would still be the same. The longest unival path would still be the same, and it wouldn't be starting at the root, nor would it be ending at a leaf. So in general, what will the longest unival path look like? The general shape of it, like the most generic shape that it could have, would be perhaps something like this. So I'm putting dots here because it doesn't have to end at the leaf. So in fact, let me not even put the dots, so that it's very clear that the generic shape would be of this kind. When we were looking at the diameter problem, the path had to start at a leaf and end at a leaf. So now it could end anywhere. But it is still an inverted V path. So we know that a top-down approach would not be suitable for it because of this kind of a shape. So let's see if we can uh, take the global problem and formulate a local version of it. The global problem is to solve for the longest unival path. The word longest is indicating that it's an optimization problem, maximization problem. How would we solve this using a decrease and conquer approach? So if this is me, I'm a lazy manager, I have a left subtree and a right subtree, and I want to find out which is the longest unival path in this tree, potentially of this shape, which has the maximum length. In what way can my node be involved in that path? Well, the path could go through my node. So if it goes through my node, it would look maybe something like this. And so if I can calculate the length of the longest unival path passing through me, so the longest unival path with my node at the cusp, and of course we are supposed to turn the length of the path, then things would work out. Because we could compute the global answer by taking every single local answer and taking the max of all those local answers. Similar to what we did with the diameter problem. So the question is, how would we solve this? As I said, an inverted V path means we would have to go bottom up. So what information do we need from the subtrees to our left and right that would help us find the longest unival path through our node? So if this green path is the longest unival path through our node, what can we say about the portion of the path inside the left subtree or the portion of the path inside the right subtree? Because that's the information we need from our two subordinates, right? What can we say about these paths? So if we look at uh, this this portion of the longest unival path, which is inside those two subtrees, it's clear that it should not be possible to extend. Well, firstly, the path starts from the root. That's clear. It should not be possible to extend this path in a way that it remains unival. Because if we could, then what we started out with would not have been the longest unival path. There would be a contradiction there. So this must be the longest unival path from the root down to some node inside this left subtree. Same thing with the right subtree. So at least we can capture that. This is the longest unival path from the root down to some node inside the subtree. Longest mean path from the root down to some node inside the subtree. So if we could get that information from our two subordinates, then we could take um, that path, add a 1 and add a 1 on this side as well, assuming that our node has the same value, right? Assuming that incorporating a node into that path would create a longer unival path. So obviously the values that are here need to match up with the values that are there and also with the value at my node. So if those things work out, then we would be able to get the longest unival path through me or my node. So let's give this a name. Let's call this, let's say the unival height or something of a subtree. The unival height of a subtree is starting from the root. What's the length of the longest unival path down to some node? Okay, so we also have to pass the same information up to our manager. So apart from computing the local answer, we would have to figure out what is the longest unival path from the root down for my subtree. So that means if we have this length and we have this length, we would have to pick the larger of those two. Something like that we would have to do. So it looks similar in some sense to the diameter problem, but of course the unival property makes it uh, more tricky. So let's try to figure out how we may implement this by writing the helper function code as usual. So we're going to make those two recursive calls. If my left subtree exists, then I'm going to make a recursive call and get back from my subordinate um, this particular length, right? The unival height of the left subtree. Okay, it's a long name, but let me write that. Left subtree unival height. Oops, one word. Right. Same thing for the right subtree. Right subtree unival height. would be the return value from our right subordinate. And then we have to think about the post-order DFS work. So firstly, we need to figure out our own uh, subtree unival height, because again, there are two tasks to do. One is, given that we are getting this information from our subordinate, we need to pass to our manager the same information. And secondly, we need to solve our local problem. So what would be um, our own unival height? So going back to that diagram, depending on whether our value matches the value here or not, we would have either added a 1 to what our left subordinate returned, or if these two values don't match, then what would be our unival height on the left side? Well, there would be no edge in that case, so the answer would be 0 in that case. Same thing on the right side. So how do we do this then? Let's say we want to do the post-order DFS work. So once again, we could implement it in two slightly different ways. One way is that we peek down into our left subtree to see if there's a match or not. And the other is we have our left subordinate return not just the unival height, but also the value at the root. So I think in the code, I've again done it the other way, but let me take the risk of maybe trying to do the same thing that I did in the last problem. So I'm going to say that our left subordinate returns a pair, the left value as well. And likewise, the right value as well. So let's figure out our left unival height, right? We want to compute this. So if there is so the logic is as following. If there is a match between these two, then we are going to add a 1 to whatever the left subtree unival height was. So if the left value matches node.val, then our left unival height will be one more than the left subtree unival height. Right? Else, if there's no match, then it's going to be 0. So maybe you could have it 0 as part of the initialization. Likewise, if the right value is equal to node.val, then our right unival height will be one more than the right subtree unival height. So let me write the comment like this so that there's space for initialization. So we'll say our left unival height by default is going to be 0. Our right unival height by default is going to be 0. Okay, so if there is a match from the left side or right side, then we will update them to these values. Now, once we have updated them, what would be my unival height, my subtree unival height? My subtree unival height would be the bigger of those two. And that is what I would return. Right? So from this function, what I would return is my subtree unival height. So I would return the bigger of the left unival height and the right unival height. Okay, I could have written this in a separate line, but I'm just saving space here. This would be my subtree's unival height. My subtree's unival height. But not just that, we are also supposed to return the unival value, right? So because we got a pair, so the second component of that pair would be node.val, right? My own value. No space here. Okay, so now we have done the first task. We have to do the other task of computing the local answer and updating the global answer if the local answer is better than the global answer. So the longest unival path, the default value for that global answer is going to be the smallest possible length of the global answer, and that's going to be 0, right? Since the longest unival path can have a minimum value of 0. Now we'll update the global answer if our local answer is better than it. So the question is, what is our local answer? If we have our left unival height and our right unival height, then we just have to add those two to get our local answer. Left unival height plus right unival height. If this works out, we still have to do that check on what the initialization should be if it's a leaf node or an internal node with one of the subtrees missing. But if this does work out, then all we would need to do is initiate the boundary walk by running this with the root node as the parameter and returning the global answer. So let's think about that. What do we do if one of the subtrees is missing? So let's say this subtree is missing. It's not there. In that case, we want our left unival height to be 0 because there are no edges on the left side. So we would want our left unival height to be 0, similar to what we did in the diameter. Was it the diameter problem or the problem before that? I think in both we did the same thing. So we want our left unival height, this value, to turn out to be 0. So our left subtree unival height in that case should be -1. Okay, this should be -1 so that when it's added to 1, it becomes uh, 0. Moreover, we want, assuming that this runs, right? If this runs, then we want our left unival height to be updated to 0. Oh, actually, we did already initialize it to 0. So another way to think about this is, why don't we want to have it remain 0. Right? If there is no left subtree. So how do we make it remain 0? Well, maybe we don't want this if condition to be execute. I mean, we don't want the if to be true. So we don't want the if to be true, then what should our left value be if our left subtree did not exist? That means we didn't get a left subtree unival height back. We didn't get this back. We have to initialize them to something. So so I think we have two options here. If we have left val not be equal to node.val, right? Maybe we just set it to something different from node.val. Then our left unival height will end up being 0. And in that case, our left subtree unival height can be anything. We could have it be -1 or whatever it is, would make a difference. And the same thing would apply for the right subtree. So let's write that. We have the left value by default being something different from node.val. Same thing for the right value. Our left unival height will remain 0 and our right unival height will remain 0. We do have to initialize left subtree unival height and right subtree unival height also. But their values are irrelevant. You can pick whatever. I'm just going to write it as a blank here, indicating that any value would work. So I'm hoping I did this correctly. If any of you is working on typing this up already, then just let me know if this works. Do we have an edge case here for an empty tree? Yeah, we do have an empty tree. I think there was a, yeah, they didn't give a toy example with an empty tree, but if there is an empty tree, then what do we want the answer to be? So if root is null, then the longest unival path in an empty tree should basically be 0. Why node.val -1? It can be any value not equal to node.val. Yeah, that's true, Santosh. Uh, um, this didn't have to be -1. It could be any value different from node.val. We could actually look at the conditions in the problem. It says that node.val is between -1000 and 1000, so you could even just initialize it to 1001 or 2000, something like that, so that you know it's not going to be equal to any node. Should we compare left and right value before we add them to compare with the global value? Should we compare the left and right value before we add them to compare with the global value? No. No. So suppose, so let's look at that. Suppose, this value happened to match with this value, but this value did not. Okay. In that case, our left height would be correctly incremented by 1, or left unival height, sorry. Our right unival height would be correctly set to 0. Okay, because there was no match here, so it's as good as there not being any right unival path. So in that case, our longest unival path through my node would be this one. Does that make sense? So even if my right child or subordinate returned to me a relatively large unival path from the right side, unfortunately the value did not match my value, so I can't really extend it. So I won't even include it. So I wasn't consciously thinking about doing this, keeping your question in mind here. I'm just looking at what should I do on the left side, what should I do on the right side. But it turns out that uh, it works in that kind of situation where the path can be extended only on one side. So this is the most generic shape, but it can have a more specific shape, as in it can just be part of this, right, on this side, or maybe it's just looking like that. Or maybe it's not looking like anything. Maybe this value is different from both of those values. So there is really no unival path. There are no edges in the local answer for this node. It's also possible that one of these paths or both of these paths might even extend down all the way to the leaf. But all that is everything, all those special cases are captured in this generic shape. So does that make sense? I mean, this is not the kind of code that I can start by writing this first, then this, then this, then this, and then going down like this, right? Notice this is not the order in which I wrote the code. What I wrote the code in is I first wrote the template, knowing what value we need to return. And, in this case, I just suddenly decided that, okay, like in the last problem, we'll have the values also passed up in the left child and from the left child and right child. And then we think about how to use it to do two things. One is to figure out what we need to return to our manager, which is my subtree's unival height. I get that by looking at extending both of these, right? But extension can happen only if the values match. So if this value matches my value, then I extend it. If this value matches my value, then I extend the path on the right side as well. And now having extended it, I can calculate what my return value is to my manager. And then I figure out what's the local answer to my problem. It would be the sum of these two values. If these values now did not match, then I want the heights to be, the left or the right height, whichever direction it didn't match, to be 0. So then I added this initialization. I could have also added it as an else clause. If they match, then this, else I would have this line. But to save space, I just did the initialization and I had the if condition. Then once I have this, then I think about, well, what if one of the subtrees did not exist, or both of the subtrees did not exist? What do I want the answer to be? Well, I want these heights to be 0 in that case. What is the way to make those heights 0? Either I have to initialize this to -1 and this to -1, but actually this line lies inside an if clause. So if I don't even make the if clause become true, then the value it will have at the end is going to be whatever value it was initialized to. So how about I do the initialization of um, of these four, sorry, of these four variables, right, which are after all returned, and I have to figure out what they should be initialized to if those corresponding children did not exist. How about I make left val and right val such that they are never equal to, I mean, they are not equal to node dot val to start with. So that will ensure that my left and right unival heights will remain 0, which is what I want. And that's why I picked a value that's different from node.val. The other two doesn't matter. Pick whatever you want. Because the only time they will be used is when these two are equal. And if these two are equal, that means we did have a left subtree or a right subtree, in which case these variables would have the right values anyway, coming up from below. So unless I missed something, I think this should also run, although that's not how I have done in the actual code here. I think this is a little better because I'm sort of preserving the structure, two recursive calls followed by all the post-order DFS work at the end. So the time complexity and space complexity are the same as before. Because the argument is the same. Every line inside the red box runs in constant time. Okay, should we move to the next problem? Or are there any questions? Okay, let's move to the next problem then. So in the next problem, we are given a binary tree and we are given two nodes that actually exist in the tree. And we need to find their common ancestor, the least common ancestor in the tree. For example, if you're given this tree and you're given these two nodes. Okay, so along with the tree, there are two additional parameters that are given to you, two individual tree nodes, which are known to exist inside the tree. We need to find the least common ancestor. So we need to find a common ancestor that is as low as possible in the tree. So this is the only common ancestor, in fact, in the tree. So this would be the output. Also, looks like you have to output the number. Is it the number or the node? I think probably the node. Let me see here. Uh, yeah, you have to output the node. So reference to the least common ancestor node, not just the raw integer value. So least common ancestor means that let's take this example, 5, 4. Oh, okay. So in this case, um, one of the nodes is the direct ancestor of the other. So the least common ancestor would be, that node itself. Likewise, if the tree looked like this, and you're asked to find a common ancestor of 1 and 2, it would be the reference to node 1. But suppose in this tree, we were asked to find the least common ancestor of, uh, let's say, 6 and 4. So that would be node 5. It's a common ancestor, and it's a common ancestor that's as low as possible in the tree. the root is also a common ancestor of 6 and 4, but it's not the lowest common ancestor because there is another node further lower than it, which is also the common ancestor of both of these. One thing they've said they will ensure is that all the numbers inside the nodes are going to be unique. So all these numbers are unique. So you can look at the integer values inside the nodes to uniquely identify them. And it's guaranteed that the two nodes whose lowest common ancestor you're asked to find out will both exist in the tree. So how would the lowest common ancestor be represented? If we were to show it in a generic diagram, if this is the lowest common ancestor somewhere inside, uh, so we are going to have P on one side and Q on the other side. Okay, we can't have P and Q both on the same side because in that case, this would not have been the lowest common ancestor. Both of them lie within that subtree, then there would be another common ancestor lower than it. So they should lie in two different subtrees of the LCA. So for us to identify this lowest common ancestor node as the lowest common ancestor, we need therefore information from these two different directions. You can see an inverted V kind of shape there. So we need to use a bottom-up approach. Okay, so we need to use a bottom-up approach, that's clear. So the global problem is to find the least or the lowest common ancestor of P and Q. Okay, those are integer values given to us, but there will be unique tree nodes that will have those integer values. So actually, hold on. Yeah, P and Q are actually given as tree nodes. Right, they are given as tree nodes. But it doesn't matter, even if they had been given as integers. We could still do it. So as a lazy manager, what am I going to do? What will I define as my local problem? So this is me. I have a left subtree. I have a right subtree. I'm interested in finding the lowest common ancestor in whatever way I can, assuming that I focus purely on my node and I get in, whatever information needs to flow up from both my subtrees. So how can I find the lowest common ancestor of P and Q? And there are two options. Either I am the the lowest common ancestor, or I am not the lowest common ancestor. So that's the only thing I could do. Determine if I am the lowest common ancestor. Let me ask it as a question. Am I the lowest common ancestor? So each manager is asking, is it me? Is it me? That's what everyone's trying to answer. So if any of them finds that they are the lowest common ancestor, then that would be the global answer. So we can say the global answer is um, it's the identity of the node which is going to return, which is going to say that I am the lowest common ancestor. Okay, so in some sense, it's like the or, right? If any of the, in a sense, we are guaranteed to find the lowest common ancestor in the tree. There's no doubt about that. We just have to identify which specific node is the lowest common ancestor, right? Whichever local answer um, whichever local answers, whichever local answer uh, is the LCA. So exactly one of those local answers will be the LCA. So um, how do we then solve this local problem? How do I determine if I am the LCA of P and Q? What information do I need from the two subtrees that will help me figure out the answer? Am I the LCA of P and Q? So if I'm the LCA, clearly both, P should exist in one of these two subtrees, and Q should also exist in one of these two subtrees. Right? So what I want from my left subordinate um, is there a P in your subtree? Or is there a Q in your subtree? Same thing from my right side. Is there a P in your subtree? Is there a Q in your subtree? I want answers to both of those questions. Because P could be on the left, Q could be on the right, or maybe P could be on the right, Q could be on the left. Maybe both of them are on the left, both of them are on the right. So we can't predict which direction. I mean, whether P will be found or not found, and if it is found, it could be in either the left subtree or the right subtree. So from both subtrees, we want a flag that tells us is P there and is Q there. If we find both P and Q in either of those subtrees, then clearly we are a common ancestor. The question is, am I the lowest common ancestor or not? How do I know if I'm the lowest such common ancestor? Well, there are two ways to think about this. In the diagram that I drew here, the lowest common ancestor will have P and Q in different subtrees. That's one way to think about it. Another way to think about it is, because we are going bottom up, if somebody before me found that they are the lowest common ancestor, or found before me even the fact that they are the common ancestor, then I cannot be the lowest common ancestor. If you think about how post-order DFS or post-order bound traversal would work, like around the boundary walk, we are going to hit the lowest common ancestor the right protrusion of the lowest common ancestor before we hit the right protrusion of any ancestor further up in the tree. So the very first manager who finds that they are a common ancestor of P and Q would be, would have also found the lowest common ancestor. Lowest common ancestor would be the first common ancestor that would be discovered along the boundary walk. So either way, whether you check for, if both P and Q are there, if they are in different subtrees, then I'm the lowest common ancestor. Or you don't even check if they are in the same subtree or not. If there is no one who has stamped their name inside that global mailbox, I am the first one uh, to discover that I am a common ancestor. I can just put my identity in that global mailbox. Anybody else who comes later than me checking that mailbox is not going to overwrite it, because they would have understood that, okay, there was somebody here before me, so uh, I must not be the lowest common ancestor. I am a common ancestor, but somebody was here before me. So okay, so um, that seems to clarify how things would go here. So um, the questions, the answers that we need from our two subordinates are answers to two questions. Um, is there a P, or is P in your subtree, and is Q in your subtree? Those are the two answers we seek from our uh, left subtree and our right subtree, and so we have to come up with the answers to these questions in our subtree. Okay, so if P is found here, obviously P is also found in my subtree. If Q is found here, or if Q is found here, if either of these Boolean flags is true, then that means Q is also found in my subtree. But maybe P was neither here nor there, but P is there in my node. So then also I would tell my manager I found a P in my subtree. Okay, so it's all common sense here. We just have to code it up. So let's do it by going back to the template. So an arbitrary internal node manager is going to start out by making those two recursive calls. So if there is a left subtree, make a recursive call, get back those two Boolean answers. So if there is a left subtree, get back the two Boolean answers. What are those two answers? P in left, Q in left. Right? These will be true if those nodes are found in the left subtree. This is going to be the return value from making the recursive call. If node dot right, if there is a right subtree, Then I have two more Boolean flags here. So that's our template. And now we think about our post-order DFS work. So task one out of those two, the first task is to figure out the return value uh, to send up to our manager. The return value is P in my subtree and is Q in my subtree. I need to uh, send up those two Boolean answers. So let's say I'll say found P. If P is found in the left subtree or P is found in the right subtree or my value is P, then I can declare that I found P. Right. So P in left or P in right or my value is equal to uh, P dot val. So if P and Q were given as raw integers as input, then I would just have P here. But they're given as references to tree nodes, so I'll just look up the integer value by doing P dot val. Same thing for Q. Found Q is the same as either finding it in the left subtree or finding it in the right subtree or finding it inside my node. What am I going to return to my manager? I'm going to return these two Boolean flags. Found P, found Q. So I've completed task one. Now I have to figure out if I'm the lowest common ancestor. Out of the two options I had mentioned, so one of them was P and Q are found in different subtrees. There is actually a more complicated scenario where I think in one of these examples we had that 5 and 4. Right? So it's possible I find P inside my node and Q I found in the right subtree and so on. So there are those different kinds of cases which I don't want to deal with. So I'm just going to keep it simple and say if I found P and Q, both of them in my subtree, then I'm a common ancestor. And if nobody in that global mailbox has uh, identified the common ancestor yet, then I'm putting my stamp there. So the global answer, let's say it's null to start with. Nobody has put it there. And I find that P is in my subtree, sorry, P is in my subtree and Q is in my subtree. And nobody has identified the common ancestor yet, then I know I'm the common ancestor. It's going to be my node. So now all I need to do is to call this with the right parameters. For the root node, it's going to be the root. And at the end of this, the global mailbox would have the answer. So we just return that. Time and space, same as before. Any questions about this? Okay, so example 2, let's say P is 6 and Q is 4. Why can't LCA be 3 and 3? 3 is less than 5. No. So in this example, if 6 and 4 were P and Q, then the lowest common ancestor is 5 and not 3 because 5 is lower in the tree. We're talking about the level of 5. We're not talking about the value. We're not comparing the value of 5 and 3 to decide who's the lowest common ancestor. Lowest means most recent common ancestor. If you were to think of uh, parents or ancestors giving birth to children here. If this was a family tree, we're talking about the most recent common ancestor in the tree. In other words, the common ancestor whose depth in the tree is the highest. In example 3, if P is 1 and Q is 2, how is the LCA 1? Well, if P and Q share a parent-child relationship, then their common ancestor is going to be the parent, right? So the parent itself is the child's ancestor. So the common ancestor of the parent and the child is going to be the parent. So what I'm saying is the least common ancestor of a parent and a child is the parent. So basically you trace a path from any node up all the way up to the root. Do that from both nodes. Whichever is the first node that is common to both the paths, that would be the LCA node. So in case you're confused by this because you're thinking that the common ancestor can't be, I can't say that I am the common ancestor of myself and my kids. Um, well, in a sense, I can claim that, but it's not like the common ancestor has to be different from both of these nodes. It can be the same as one of them. How are we ensuring that P and Q are not in the same subtree? Is it because the LCA is none? So if P and Q, so P and Q will be in the same subtree for 3 here, right? If 6 and 4 are P and Q, then when we are doing the post order work for 3, we are going to find 6 and 4 both in the left subtree. But if they are both in the same subtree on the left side, it means that 3 cannot be the lowest common ancestor, because if you go down to 5, for example, 5 is a deeper node, which is also the common ancestor of 6 and 4. So we are not doing anything fancy to ensure that P and Q are not in the same subtree. All that we are saying is, given that the boundary walk is going to hit the right protrusion of 5 before it hits the right protrusion of 3, automatically we are going to um, exit the tree of the lowest common ancestor before exiting the tree of ancestors further up. By the very fact that we are doing a bottom-up traversal here, the lowest common ancestor will be the common ancestor that's found furthest below. That means we will be exiting their subtree before exiting the subtrees of ancestors further up. So the first person who finds themselves to be a common ancestor of P and Q, or the first person who finds P and Q both in their subtree, is going to be the lowest common ancestor. So that way we don't have to worry about, oh, okay, is P in my value, in my node, and Q in one of my subtrees, or is Q in my node, is P in one of the subtrees, are they in separate subtrees under me, or are they in the same subtree? Doesn't matter. As long as both of them are in my subtree, and as long as nobody has identified the common ancestor yet, I can raise my hand and declare myself the common ancestor, or as in the code here, I just go and take ownership of the global mailbox. So this if statement is going to be true only once in that entire boundary walk. Anybody who's not the common ancestor, obviously, they are not going to find this to be true. And anybody who is a common ancestor but not the lowest common ancestor is also not going to find this to be true, because this is not going to be null. Any other questions about this? Okay, no. So then we can go to the next problem. Validate binary search tree. So far, all the problems we have done involved binary trees or n-ary trees. They were not search trees. Now we are trying to figure out if a given binary tree is a search tree. A search tree has a search property, which is what we have to test for. The search property is that if you take any node, all the nodes in the left subtree are going to be smaller than it. So in this problem, I think all the nodes, okay, they don't have to be distinct, is it? We haven't mentioned it. So assume that the values are all distinct. So all the values in the left subtree should be less than the value at the node, and all the values in the right subtree of a node should be strictly greater than the value in that node. And this should be true for every node in the tree. If it's true for every node in the tree, then we can do binary search in order to search for a particular value in the tree. We start from the root, we check if the key that we are searching for, well, if it's there in the root, then we are done. But if it's not there in the root, we know that all values in the left subtree of the root are smaller than it. So if the key we are searching for is smaller than the value we see in the node, we know that it will be found in the left subtree of that node. So we go down to the left subtree and look at the root of the left subtree and keep repeating this, right? This is basically binary search, but on this linked structure of a tree instead of doing binary search in a sorted array. So we just have to validate if a given tree is set up as a binary search tree. Does it have this search property? So in this toy example, the first tree is a binary search tree because when you look at this node 2, everything in the left subtree of 2 is smaller than it, everything in the right subtree is bigger than it. There's nothing further to check. In the second example, let's look at the root node. Is everything in the left subtree of 5 smaller than it? Yes. Is everything in the right subtree of 5 bigger than it? No. We see 3 and 4 in the right subtree. That's not allowed. So the answer is false. So in a sense, this problem definition itself is telling you, what each local problem is going to be. So the global problem is determine whether the given binary tree is a binary search tree. The local problem is every manager is going to try to, ensure that this property is true for them. Everything in my left subtree should be smaller than my value. Everything in my right subtree should be bigger than my value. And both my left and right subtrees should be binary search trees. So if every manager is checking for this property and everyone finds this property to be true, then the tree as a whole is confirmed to be a binary search tree. Okay, so the global problem is determine if it's a global problem. Is the given tree a BST? Okay, the local problem is, are all the given properties true for my node? So if I am a lazy manager, I have in general a left and a right subtree, what is my local problem? To verify these three properties. Are all the three properties true for my node? So the global answer is something that can be constructed by aggregating all the local answers. So every single manager should find that the three properties are true for their node. Then the global answer would be true. So again, the global answer would be the AND of all local answers. So let's think about what a manager would do to go about solving their local problem. How do I tell if all three properties are true? How do I tell if the left and right subtrees are also binary search trees? Well, that's not my job. That is something I expect my two subordinates to come back and tell me directly. This information I get directly from my subordinates because I don't want to look into their subtrees. Once again, we, in order to solve the local problem, we have to look on both sides, right? And we have to look into both subtrees. So this is not something that, at least naturally, uh, I would use a top-down approach for. Although it's not impossible, maybe, but at least it's not something that naturally comes to my mind. Whereas looking at into both subtrees, that's something that I think I can, easily map to a bottom-up information flow. So I'll get this from my two subordinates. Now I also need to verify that on my left side, all the values are strictly less than my value. And I need to do it without looking inside the left subtree. Without looking inside this left subtree, I want to figure out if all the values in it are smaller than my value. So what summary information can I request my left subordinate to give up to pass up to me so that I can confirm that all the values in my left subtree are strictly smaller than my value. Yeah, if the largest value in the left subtree is smaller than my value, then I know all the values in the left subtree are smaller than my value. So I expect my left subordinate to also pass up to me the maximum value in their subtree. Similarly, on the right side, I want to verify that all the values in the right subtree are strictly greater than my value. So without peering into the right subtree, what information should my right subordinate pass up that will allow me to check if all the values there are larger than my value? If my right subordinate passes up to me the smallest value, the minimum value in their subtree, and if that minimum value is still greater than my value, then I know that all the values in the right subtree are bigger than my value. So I need the max value from one of my subordinates. I need the min value from one of my subordinates. I also need from both of them um, confirmation of the fact that those subtrees are individually binary search trees. That's the third thing. So that means a subtree in general is expected to pass what kind of information up to their manager? The maximum value in their subtree, the minimum value in the subtree, and the answer to the question, is that subtree a binary search tree? So there are three pieces of information that need to simultaneously be handed up in order for any manager to solve their local problem. Which means each manager has to pass up to their manager these three same pieces of information inside their subtree. So let's start writing the code and we'll know exactly, how to do that. We'll follow the same template. So we'll write the general code from the perspective of an arbitrary manager who's going to start out by making those two recursive calls. So if they have a left child or a left subtree, then we'll make a recursive call and we expect to get back these three uh, pieces of information. Namely, what's the smallest value in the left subtree? What's the largest value in the left subtree? And is the left subtree a binary search tree? So this is what I get back from my recursive call. Same thing from my right subtree. Sorry, I need to close this and reopen this because some trouble with the software here. Okay, node.write is not null. I want to get the minimum value from the right side, from the right subtree, maximum value from the right subtree, and whether the right subtree is a binary search tree or not. These are the return values from making a recursive call or delegating the work to my right subordinate. Now comes the post-order work. So what work do I do? I have two tasks. The first task is to pass up to my manager the same three pieces of information. The second task is to determine if uh, the BST property holds at my node. Actually, if the if the BST property holds at my node and my two subtrees are binary search trees, then the subtree rooted at my tree is also a binary search tree. So then I would know whether my subtree is a binary search tree or not that way. So anyway, the three pieces of information. How do I figure out what's the minimum value in my subtree? My subtree minimum. Well, the smallest value in my subtree is going to be uh, the smaller, I compare the minimum value in my left subtree, the minimum value in my right subtree, and the value at my node and take the smallest of those three. So the min of my value, the minimum value in my left subtree, and the minimum value in my right subtree. That's my subtree minimum. Likewise, my subtree maximum, the second piece of information I need for my manager, is going to be the max of my value, the maximum value in my left subtree, and the maximum value in my right subtree. How do I know if, let's see, Yeah, how do I know if I am a binary search tree, or the subtree rooted at me is a binary search tree? These three properties, if they hold at my node, this is equivalent to saying my subtree is a BST. Right? How do I know if the subtree rooted at my node is a binary search tree? So if my left subtree is a binary search tree, my right subtree is a binary search tree, and the smallest value on my left subtree is less than my value, and my value is less than the largest value in my, sorry, I'm saying it the other way. If the largest value in my right subtree, sorry, in my left subtree, if the largest value in my left subtree is less than my value, and my value is less than the smallest value in my right subtree, then the subtree rooted at my node is a binary search tree. So if my left subtree is a binary search tree and my right subtree is a binary search tree, and the largest value in my left subtree is less than my value, which is less than the smallest value in my right subtree, then uh, so is right BST, is left BST. Maybe I'll call this MI a BST. This is true. Else MI a BST is false. So what am I returning up to my manager? All these three pieces of information. First, the minimum value in my subtree. Maximum value in my subtree. And a Boolean flag indicating if the subtree rooted at my node is a binary search tree. So in what way do I now contribute to the global answer? Global answer is the AND of all the local answers, where each local answer is, are all the three properties true for my node? That means this is equivalent to saying, is my subtree a binary search tree? Right? This is equivalent to saying, is my subtree a BST? So if every single subtree is a binary search tree, then the global answer will be true. So by default, we should initialize it as true. And if any of the managers finds that their subtree is not a binary search tree, they'll go and permanently, flip the switch to false. And once it's false, nobody can set it back to true. So in this case, if I find, for example, that my binary search tree, my subtree is not a binary search tree, then I can just go and set the global answer were false, assuming that it's initialized to true. So this is going to be the red box. I think in this problem, because they're going to give you a tree that has at least one node, I don't need an empty tree subcase, sorry, edge case. I do need to call this with the right parameter to launch the boundary walk and then return the global answer. Okay, but one thing I didn't do is to make sure that this works even if one of the two subtrees or both of the subtrees are missing. So we want this to work even in that case. So let's think about the initialization of these parameters. If one of the subtrees, at least one of the subtrees, did not exist. So what should the minimum value in the left subtree or the right subtree be initialized to if those subtrees don't exist? Or let's think of a case where both subtrees don't exist. It's a leaf node. What's the minimum value in the left subtree or the right subtree? The minimum value should be such that when I use those values for computing the minimum in my subtree, the winner should be my value. The winner should be my value. So the initialization should be such that the min values by default are going to be smaller than any value that can exist in a node. Let's see, node.val is, it can be as small as minus 2 to the power 31. So let's just go down to minus infinity. Sorry, I think I made a mistake with the min and max. I want the minimum value to be my value. So my value actually has to be the smallest value among these three, right? If I'm a leaf node, I don't really have a left and a right subtree. So I have to pick these two minimum values such that the minimum of all three is always going to be my node. So my node has to be the smallest. My node's value has to be the smallest. So the min left and min right have to be actually bigger than the biggest possible value. So min left, let's call it infinity. Min right, initialize it to infinity. Any integer greater than the largest possible value. My subtree maximum should turn out to be my value if I'm a leaf node. So when I take the max of my value and these two values, it should always be my node, irrespective of what my node's value is. So if these two are initialized to minus infinity, that will always end up being the case. So max left is going to be minus infinity, max right is going to be minus infinity. So that will make sure my subtree min and max turn out to be correct. How about this calculation? Am I a BST? If I don't have the two subtrees Am I a BST? Yes. Well, an isolated node by itself is a BST. So that means this if condition should end up being true. Now this is already going to be true based on how we have initialized it, because this is going to be minus infinity. This is going to be my value. This is going to be plus infinity. So this is already, just by trying to make this work out, this is already worked out. So we need both of these to also be true. So is left BST is true, and is right BST is also true. So that will make things work out for the leaf node case, or even an internal node case where one of the two subtrees doesn't exist. So time and space will be the same as before. The code that I've written is something I just uh, verbalized in just talking through the problem. It can be made more compact, as in, if you think about it, if this property is violated at a node, then clearly the answer is false. But if you look at the ancestors, any of the ancestors of that node, um, even if they are not notified that this subtree is not really a binary search tree, and even if they just look at this property and they find that okay, it holds at their level, we would still get the right global answer. In other words, what I'm saying is this can be removed. All of this can be removed and still the code would work correctly. Why is that? Because suppose the entire tree is not a binary search tree. That means there is some violation somewhere. What sort of violation is that going to be? It's going to be a violation in this condition somewhere. So whenever this violation happens, if we set the global answer to be false there, we will catch that violation. We don't need to, like, even if I, as an ancestor node, I'm unaware of the fact that inside one of my two subtrees there has been a violation. But whoever detected the violation inside those subtrees, they would have flipped the switch to a false. So unless I have to determine that whether my subtree is a binary search tree or not, I don't need that information. What I need to ensure, strictly speaking, are these really actually these two properties. Okay, even if we eliminate this, it doesn't change anything. If these two are true, this will always be true. right? If these two are true for every node in the tree, then this will always be true. So the third property, in a sense, is a redundant property for the entire tree to be a binary search tree. For a subtree inside that tree to be a binary search tree, we need these two properties to hold for every node inside that subtree. If they hold for every node inside that subtree, then the subtree as a whole will be a binary search subtree. Does that make sense? I just followed these three properties because that's what was written in the problem statement, but we can actually cut out some of the work and still have things give us the right answer. Any questions about this problem? Why? Uh, Smita asked, wouldn't the min value be always from the left subtree and the node itself? Why do we compare the right side? Um, so that is if the subtree is a binary search tree. Otherwise, it won't be true, right? We want to return to the manager the min value in our subtree, and that should work. It should be the correct answer, irrespective of whether our subtree is a binary search tree or not. Does that make sense? That's why we also have this and not just these two. Yeah, go ahead.
Oh, well, actually, if it fails, wouldn't we anyway update global answer to be false? So we would never reach this situation where you're saying we have to compare the right side.
Are you assuming we would bail out early?
Yeah, I mean, the first time you hit left greater than right, your global answer is going to be false anyway. So we'll never reach this line. My subtree minimum is equal to min of 3 values. You would only reach for 2 values.
So we will reach. So the boundary walk is going to be fully done. We are not bailing out of the boundary walk if so similar to the very first problem we did, which was also a decision problem where a bunch of you said that we don't need to do something, we could return straight away. True, but it doesn't change the asymptotic complexity to do the whole thing. And um, if that was the only problem you were solving, or if you were actually building something where this is the specific problem you're trying to solve, then bailing out early would make sense. But because there are a large number of problems of this kind, many of them are counting optimization problems. Um, we we want to write the code for all of them in the same way so that there is less cognitive load on your brain to think about what to do. So
Okay.
not just that, you'll see the very next problem we do is going to be a slight extension of this where we simply cannot bail out early, because even if we discover that a subtree is not a binary search tree, um, we still want to keep going because we want to find the largest binary search subtree inside a given tree. So then the code for this would have to be written you know, in a way that wouldn't exactly match the code for that problem and for other problems. right? So, but you're right that when there is a decision problem where the global answer is the AND of a bunch of local answers, a single false local answer essentially decides what the final global answer will be. And so all the work that is going to be done from there on is redundant. So if you can uh, bail out early, that's fine, and probably the way to go if these decision problems were the only problems you had to face. So if you're comfortable doing that, you can add that in and modify this code. But if you don't, if you're not confident that you would remember to do things in without having any errors with test cases and all for the different trees problems, then it's good to stick to this template and just go through the whole boundary walk, even if you know that you have the final answer beforehand. Since the asymptotic complexity is unaffected by it, because any code that you write for micro optimizing and bailing out early, that code can be bypassed by an adversary who could give you a worst case input, a tree where, let's say, it is a binary search tree, in which case, the whole code, the whole boundary walk will be done. So the worst case complexity doesn't change from that. Is that okay?
Yeah, okay.
Yeah. In the conditional check for valid BST, should it not be max left is less than or equal to node.var and same for right side? Yeah, the less than or equal to, well, in this lead code problem, they have strictly less than and strictly greater than. That's why I haven't added less than or equal to or greater than or equal to. Any other questions? All right. So let's look at the next problem. It's, as I said, related to this one. It's about finding binary search subtrees um, inside a given tree, even if the entire tree is not a binary search tree, there might be subtrees inside which could be binary search subtrees. So we want to find the largest subtree inside a given tree, which is a binary search uh, tree or subtree. Okay, so for example, in this toy example, um, let's see, what do we have to return? I think we have to return the count. So you have to return the size of the largest binary search subtree. So let's see here. So in this first example, the entire tree is not a binary search tree, because if you look at this root node here, which is 10, everything on the left side is smaller than 10. But on the right side, not everything is larger than 10. You see a 7 here, which is smaller than 10. So the property is violated uh, when you look at the root node. But if you look at this subtree, this smaller subtree has a root called 5. And on the left side, you have 1. On the right side, you have 8, which is bigger than 5. So the left subtree is smaller, right subtree is bigger than 5. So this subtree satisfies the binary search tree property. And it seems to be the largest subtree that satisfies the binary search tree property. So the output, I think here would be a 3. In the next example, let's see, 427,235. 427, 23, 5 null, 2 null, null null, null null, and 1. So in this example, let's see, the whole tree is not a binary search. Oh, is it? No, it's not. So the whole tree is not a binary search tree because the root node is 4, and in the right subtree, no, it is. In the right subtree, you find all values more than 4. Okay, I think here they are using the strictly less than. So the left subtree values should be less than the value in the parent root. So that's clearly not true here. Left subtree has a value that's equal. This has a value that's equal. So the smallest subtree, which is a binary search tree, is this one. A 2 with a left child of 1. Also this one, a 7 with a left child of 5. But anything bigger, that's not true because there's violation happening within the subtree. So what we want to do is to identify the largest binary search subtree, the size of the largest binary search subtree inside the given tree. And we want to do it with big of theta of n complexity, worst case. So once again, given that we have to think about subtrees, it makes sense to go bottom up. So if we have ourselves as the root manager with potentially a left subtree and a right subtree, and we ask how can we solve this problem of figuring out which is the largest binary search subtree inside the overall tree. What can I do here if I were to use decrease and conquer and focus only on my node? So either the tree rooted at my node is a binary search tree or it's not. So what I could do is I could ask the question, is the subtree rooted at my node a binary search tree? If it is, and if I know the size of that subtree, then I can determine whether the subtree rooted at my node is the largest binary search tree or not. So this is an optimization problem globally. And so we have seen from the count unival subtrees problem before that there are really n subtrees in a tree with n nodes. So if every manager is taking responsibility for a separate subtree and they are figuring out if that subtree is a binary search tree, then for those who do detect that their subtree is a binary search tree, we could use their size to determine the global answer, because the maximum size among all those subtrees would be the global answer. All right, so the global problem is to find the largest sized VST inside the given tree. The local problem would be if, is my subtree BST? If yes, um, if yes, I'm going to use its size to influence the global answer. Is it the largest BST? So the global answer is the max of all local BST BST size, sorry, max of the sizes of all local answers, right? How do I put it? Max of all local answers representing BSTs. Or binary search subtrees. We have actually written the code for determining if a given tree is a binary search tree, and we actually did it by going bottom up, and each node, each manager was determining if the subtree rooted at that node is a binary search subtree. Right? Even though I said you don't need all this information, that's assuming we are only interested in the global answer. We're not interested in the local answers. Because locally we could just check this everywhere, and that would tell us if globally the tree is a binary search tree. But if we want to figure out if locally the subtree in its entirety is a binary search tree or not, we do need this information from our left and right subordinates. We need to integrate that information to determine if the entire subtree rooted at our node is a binary search tree or not. So actually, in a sense, we've done most of the work that's needed to solve this problem. All that we need to do is, once I figure out that I am a binary search tree, I need to check if my size makes me the best contender for the global answer. So apart from determining all that we are doing here, so everything that we've done in this problem, in the previous problem, is relevant and needed for this problem as well. Because this question is a prerequisite to then find the largest BST in the tree. So assuming that my subtree is a binary search tree, if I could determine the size of my subtree, then I could tap into that global mailbox, which would now have the size of the largest BST that has been found so far. And let's see, did I write max here? Yeah. And if it's bigger than the maximum available so far, then I would overwrite it. Sorry. So why don't I just modify this answer or change this answer in a different color? So what is the extra information that I need from my subordinates to determine if the subtree rooted at my node is the largest BST or not? Well, firstly, I need to determine if it's a BST. For that, I needed from my subordinates what's the maximum value in their subtree, what's the minimum value in their subtree, so that I could use it to verify this property at my level. I also needed to know from them if they are a binary search subtree, because if they are not, then obviously I am not. Now, what additional information do I need to determine if I'm the largest binary search subtree? I need to be able to calculate my size. To calculate my size, I need to know from my left and right subordinates what are the sizes of their subtrees, so that I can add those numbers up and I can add one more for including my node, my root node, and that would give me my size. And it's my size that's going to uh, determine the global answer, not a Boolean tag like we had. Right? So this, let me make the changes in pink here, or maybe green. Green would. No, let me do pink, because I think this, in this problem you can have an empty tree. So this would go away. Okay, so what we are doing here is if I am a binary search tree, so first of all, we need a fourth piece of information from our subordinate about what the size of their subtree is. So min left, max left. How about I also add a size left and a size right? So my subtree min, my subtree max. Well, in a similar way, I would add my subtree size. There's a space here. Let's see if I can just insert it here. So my subtree size will be the sum of the sizes of my left subtree, right subtree, and one more for my node. So that goes there. That piece of information is something I'm going to pass up to my manager. So that's completed the first task. For the second task, I need to use this to compute my local answer. So my local answer is going to be, if so, my local answer is going to be important only if this is true. So in a sense, this is where I can write a comma here or a semicolon, so that I can write a second statement here. If my subtree size is bigger than what I see in the global mailbox, then I'm going to overwrite what I see in the global mailbox with my subtree size. right? I'm going to peep into the global mailbox only if I'm a BST. If I'm not a BST, then I cannot influence the answer. So here I'll say the global max. So the global max, so again, this won't be there in the is BST problem. So the maximum size is something that should be initialized to a number that can be beaten by even the smallest binary search tree, size 1. So it can't be, the size of the largest BST cannot be less than 0. So 0 is the minimum possible value. That's what I initiate the global max value to. And I update it here. Sorry, not here. I update it here by saying if I find that my local answer, which is my subtree size, is bigger than the global answer, then I update the global answer. And here I'm going to return global max value. Moreover, here you can have an empty subtree. So I will also need that line saying if the root is null, we return a 0, the size of the largest BST inside an empty tree. The thing that we have to still ensure is if one or more of both subtrees don't exist, um, are there any other further adjustments needed to the pink code? Well, these two have to be initialized. They will be set if these subtrees exist. But what if these subtrees don't exist? What value should size left and size right have if our subtrees don't exist? Well, let's look at how they're going to be used. They're going to be used to find the size of my subtree. So if I don't have a left subtree or a right subtree, it's clear that the value that should exist inside these variables is 0. So that's what I will initialize. So I'll, oops. So um, along with these 4 initializations, we'll also have size left is 0 and size right is 0. So these changes don't change the time and space, which are the same as before, but we do end up solving the problem. So I'll just add here that look at the pink changes. Okay. Any questions about this problem? Hopefully now you also see why bailing out early is something that is going to help you only for 1 or 2 problems. A small change where the Boolean problem is changed into a counting problem or an optimization problem. You can't bail out in that case. And sometimes it can even be confusing. Um, for example, in the count unival subtree problem, we had to count all the unival subtrees. Um, Suppose you found at some point during the boundary walk that your tree is not, your overall tree is not unival. Maybe we did actually do that problem, although we solved it, I think, using maybe breadth first search in the very first session. Given a tree, determine whether it's unival or not. It can be done using breadth first search, top-down DFS. It can also be solved using bottom-up DFS. If you had used bottom-up DFS, it's a decision problem, so you could bail out early as soon as you see your second value. But think about the counting version of that. Count unival subtrees. Now you're given a tree. You don't have to determine if the entire tree is unival or not. You want to count the number of unival subtrees in it, which was one of the problems we solved earlier today. So if you get sidetracked and you decide to bail out early just because you realize that a tree isn't unival and so it's not going to add to the count, right? Suppose you decide that. The problem is that the leaf level nodes are all individually unival subtrees, as you might remember seeing earlier today. So even if you know in advance that a subtree is not unival, you still want to do the entire boundary walk because you still have to make those recursive calls down to the leaf level nodes in order to collect all of them, because they will be adding a bunch of more ones to your global count. And so it's easy to just get distracted, maybe during a time test you have some anxiety and you overlook that fact, that maybe you're not able to think that specifically or that sharply about whether you should bail out or not. Well, just don't bail out. um, get the code working with the right asymptotic complexity by making sure that the entire boundary walk is done, and that way you're less likely to make errors. More important to get that correct than trying to micro optimize and then risk your code not running correctly. If you cannot return a tuple, then you could return an array with more than 2 elements, 4 elements in your language. Or you could just create you could create a temporary class or something. All right, there are no questions. We can go to the last problem for today. So here you're given a binary tree and you're asked to find the maximum path sum, where the path sum of a path is the sum of the nodes value along the path. The path sum of a path is the sum of the nodes value along that path. Now we've done a bunch of problems last week which were called path sum 1, 2, 3. But there's a difference here. The paths in this problem don't have to be ancestor descendant paths, as was the case with path sum 1, 2, and 3. A path here is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. It doesn't say that the path has to purely go up or purely come down. It can be a path that is like an inverted V. So let's take a few toy examples here. What's the maximum path sum in this tree? So think of a path whose sum is the maximum here. So if we just take this path, for example, some of the nodes that we see along the path would be 2 plus 1 plus 3, which is 6. So that's the maximum path sum, because in fact that's the longest path, the only path that exists in the tree, which is as long as possible. And you can of course have two shorter paths like this, but if you want the maximum path sum, you have to elongate it. Actually, if this had been a negative 3, okay, and that's one of the reasons why this problem is hard, is negative values are also allowed here. So if this was negative 3, and if you had looked at this path, then the sum would be 0. So in that case, we would prefer to have a shorter path, just because there are positive numbers along that shorter path. That would give us a path sum of 3, whereas this longer path would give us a smaller path sum, because we're collecting negative node values along that path. In fact, you can see a negative example here in the next toy problem. So if you want the largest path sum in this tree, you would want to avoid that negative 10. So if you look at this path, its sum would be 15 plus 20 is 35 plus 7 would be 42. That's the largest path sum. If you try a path like this, the minus 10 is still going to pull it down below 42. If you try like that, again, it's going to get pulled down. So in general, what is the shape of a path with the largest path sum going to be, or the maximum path sum going to be? It's not going to be a shape like this, right? Or a shape like that. That's still a root to, an ancestor descendant kind of path. It's going to be a path with a shape like this, similar to what I drew in that longest unival path problem. Now it could be longer than this, could be longer than this on both sides, could be shorter, maybe this is not there, maybe this is not there, maybe this node is isolated by itself, as we saw even with the longest unival path problem. In fact, with negative values in this problem, um, you can imagine a tree where there are only negative values in the tree. So you would have to pick a path whose sum is maximum. So you have to collect as few nodes as possible. because every time you collect more nodes, you're just adding a negative value, and that's decreasing the path sum. So there are issues like that to deal with. Negative numbers can also be there. Um, and the shape is general, like we had in the longest unival path problem. So how do we start thinking about this? We use decrease and conquer. And we decide that the problem looks too hard to think about as a whole. So why don't we just focus on one node, the root node, take responsibility only for that, and ask the question, in what way can this node contribute to the maximum path sum? In what way can this node contribute to the maximum path sum? It can contribute to the maximum path sum by being the cusp here of the path with the maximum path sum. So maybe the maximum path, or the path with the maximum sum, passes through that node. So if I, as a manager or the root manager, can figure out what is the maximum path sum which passes through my node as the cusp of the path, then by collecting the answers to all such local problems from everyone in the tree, we could look at which of those solutions gives us the highest path sum. That would be the global answer. So we can say the global problem is to find the maximum path sum in the whole tree. The local problem is to find maximum path sum where my node is the cusp. It's passing through my node, so obviously my node being the root node has to be the cusp of that path. Or the corner of that inverted V shape. So the global answer, because this is a maximization problem, it's going to be the max of all local answers. So at least we've figured out how the decrease and conquer approach would lead us to uh, a local problem that has to be solved by everyone. How do we solve this local problem now? What's the maximum? How do I find the maximum path sum through my node? So making my node again. Let's say this is the left subtree. This is the right subtree. And if I just imagine the maximum path to be like that, what information would I need from my two subtrees, from my two subordinates handling those two subtrees? I can't look inside those subtrees, So I need to somehow capture this information. I need to ask my left subordinate to return to me, something about this part of that path. What is true about that part of the path? Well, this path seems to be the path with the maximum path sum inside this subtree that originates from the root. Is that true? Can we say this is the path? Can we say this is the path with the maximum path sum which starts from the root? And goes down, of course. Well, suppose there was a longer path. Suppose there was a longer path which had a higher path sum, which started from the root and went down. But in that case, we could swap out this path with that path, and we would have a larger path sum for this section of the path. So when added to the remaining section, we would end up with an overall larger max path sum, which would be a contradiction, since we assumed that what I have drawn here is already the path with the maximum path sum. So I can eliminate this question mark and say that this is definitely the path with the maximum path sum, which starts from the root and goes down. And this is the information that I now want from my subordinate. What I want from my subordinate is tell me the path with the maximum path sum, which starts from the root in your subtree. Any other information we need from our subordinate? If we have that information, how can we find the maximum path sum? Well, we could potentially take that. We could obviously would have the same information coming from the right hand side. Note that here the edges don't matter, it's the numbers inside the vertices which matter. So my own node value would get added. Would that result in a higher path sum? Actually, that's not clear. Depends on what my value is. My value is a positive value, and let's say these path sums are also positive. Then yes, by adding my value to those values, we would get a higher path sum. In fact, if all values in the tree were positive, then these paths would not end somewhere in the middle. They should go down, because by visiting more vertices or continuing down to a leaf node, you'd be adding more positive numbers to the path sum. So the reason why this is complicated is because negative values are also there. And so if the value in my node is negative, maybe by including the value in my node, I could actually bring down the path sum. But that is not an option, because I'm assuming that my node must be involved in the cusp of that path. So I can't not include my node. But I can opt to exclude this. Suppose this is negative. If this path has a negative overall sum, then by excluding it, the path sum would go up. If this path had a negative path sum, then by excluding it, the path sum would go up. If both of them had a negative value, then by excluding both of them, the path sum would go up. What would the path then be? It would just be the value in my vertex. My vertex by itself would be a one node path. So these negative numbers present the main challenge here. But in either case, it looks like we don't need anything beyond uh, this piece of information from our subordinates. So let's just work with that and see where that leads us to. Like, how do we figure out what's the maximum path sum through my vertex as the cusp? By comparing maybe all these options. Maybe we include everything here. Maybe we exclude this, but not that. Or maybe we exclude this, but not that. Maybe we exclude both and just have my node value. We don't know uh, which of those options will be the best one. So we start with the helper function. So what we want from our two subordinates is the maximum path sum which starts from the root and goes down in their subtree. So if I have a left subtree, I'll hire a left subordinate, ask them to return to me the path sum in the left subtree which starts from the root and goes down. Let's call that the left subtree path sum. I just call the helper function on node.left. In a similar way, if my right child is not null, that means I have a right subtree, then I will hire a right subordinate and ask them to pass me up this piece of information, which is what's the maximum path sum in the right subtree of a path that starts from the root and goes down. And now I think of doing some post-order DFS work. How do I integrate these two pieces of information to get the maximum path sum passing through my vertex? And actually, even before that, there are two tasks, and we usually think of first calculating what is it that we have to return to our manager, because we expect this information to come up from our subordinates. So we should calculate that information to pass up to our manager. So what is the maximum path sum for our subtree, right? For this entire subtree, what's the path with the maximum path sum that starts from the root and goes down? So it can either go down on the left side or it can go down on the right side. I can't choose both. We're not talking about an inverted V path here as far as the information that needs to be passed up is concerned. that information is, a route, uh, a path that starts from the root and goes down. So we have to start from here and go down either like this or like that. So if we go down like this, we would be taking our value and adding it to the left path, left subtree path sum. If we go down on the right side, we will be taking our value and adding it to the right subtree path sum. Those are our two options. With negative numbers though, there is a possibility that both of these might have negative values, in which case we may not even want to include either of them. So in that case, we would just have the root value. So instead of two options where we add our value to the left subtree path sum and our value to the right subtree path sum, the tricky part here is seeing that there is a third option, which is to exclude both of those and just have our node by itself, which uh, is something we do because there can be negative numbers in these nodes. So my path sum is going to be the biggest of three different values. My value plus the left subtree path sum, my value, plus the right subtree path sum, and the third option is just my value by itself. This is what I'm going to return to my manager. So that's the first task. The second task is to compute the local answer to my problem, which is what's the best path, the path with the maximum path sum that goes through my node as the cusp. Now, once again, I have the option of either including this or maybe not including this, because who knows, that might be a negative uh, value. Maybe I include this or maybe I don't include it. So I really have four options. Either I include both, or I include this but not that, or I include this but not that, or maybe I don't include either. So what are those four options? Well, one option is I include both, also both paths. So let's see how to write it. Okay, let me write it like this. Either I have, you know, so I take the length of these two. So maybe the longest path through me is like that, in which case I have to add my value to the information coming from both subordinates. So the left subtree path sum and the right subtree path sum. Or maybe I just have, maybe I exclude one of them. So maybe I include just the left subtree, or maybe I include just the right subtree and exclude subtree path sum. Or maybe I exclude both of them, in which case I would have only node.val. What do I do here? I take the max of all 4 of these options. And that's my local answer. So I have to use this local answer and update the mailbox if this local answer is better than it. So the global answer will be updated if this local answer is better than it. How about the initialization here? These won't exist if the subtrees are missing. But if the subtrees are missing, we still want to compare those um, options meaningfully. So if the left subtree is missing, what should this left subtree path sum be equal to so that this still makes sense, or that still makes sense? Well, if the left subtree is missing, then this left subtree path sum should be, logically speaking, 0. So it makes sense, therefore, to set the left subtree path sum and the right subtree path sum both to 0. So assuming the global max value is initialized suitably, we will run this code with the right parameters for the route manager so that the boundary walk is launched, the depth first search happens, and at the end we will find the answer in the global mailbox. So what should the global max value be? It would be tempting to say 0. The problem is that you can't not include any node. Right? You cannot have a path with no nodes in it. Every path, because the very definition of a path is it includes vertices in it, and they even say here that you need to return the maximum path sum of any non-empty path. Now, what if all the values in the tree are negative? Then there is no way to avoid a negative answer to this problem. But if I initialize the global max value to 0, then 0 will be the output, even though it's clearly the wrong answer. So the safest value to initialize this to would be minus infinity, to make sure that it's smaller than even long negative paths in the tree. If our tree had only negative values, imagine paths, long paths in a big tree, which are purely made of negative values. Well, how low can we go? We don't know. So just setting it to minus infinity would make it safe. Maybe there is some information. Let's see. Number of nodes in the tree is in this range. The value of a node is in this range. Of course, we can't have long negative paths because you can always drop some of the vertices in that path and increase the uh, path sum. So if you had only negative nodes in a tree, then the maximum path sum is something that would occur if you picked just a single vertex in that tree whose value is as close to 0 as possible. It's negative, but as small in magnitude as possible. That would be the largest negative node in the tree. Largest means closest to 0. And that would be the answer. So what I see here is minus 1000 is smallest possible value. So if I assigned global max to minus 1001, that should also work. So I could make this minus 1001, but I'll just keep it as minus infinity. The time and space analysis are the same as before. This is going to run in linear time and linear call stack space. Questions on this problem? Oh, yes, Ajay. Ajay, you can unmute yourself.
Oh, can you hear me now?
Yeah, I can hear you.
Okay. So we have two variables here, right? My path sum, max, and then local max. Why we have to use both of them? Can't we put then my path sum the everything? Because we are passing to the global max the my path sum, the local max value.
So we don't need two separate lines here. What we can do is we can have my path sum, right? And even this, you can say, return instead of this, I can just plug in this formula.
Right. That's what
You
I'm
can
saying.
do,
Right?
yeah. I didn't do it that way so that, it's clear what this sum represents. That's what, like if you're
Okay.
reading the code. But yeah, you just need two lines here. Even this global max, you can say is max of global max, and then these four. In fact, I think that's how I have written it here.
Oh yeah.
So the global answer is the max of the global answer, and the four options, right, whose max is the local answer.
Yeah.
And
Now I
here,
get it.
so here also I don't need a variable here. You can just take this formula and bring it here.
Yeah, this was one of my Achilles heel because I always used to make mistakes in the DFS problems. So now it became much more clearer.
All right, good to know. These are bottom-up DFS problems. So, uh, the combination of top-down, bottom-up, and then we'll also look at some in-order problems. So I think we'll probably have 3 more sessions. So by the end of it, hopefully things become even more clear. Yes, Khyati?
I have a question about the validate BST in one
Mhm.
condition.
Okay. Okay.
So here for my subtree min and my subtree max, you are also looking at the node value, right?
Mhm.
So then when you check is left BST and is right BST and this range, like my current node value should be in between this range. Uh,
Mm.
that's why I was thinking that should it not be equal or should we remove the node value from the subtree? Like when we are trying to find my subtree min and my subtree max. So the question says clearly that, yeah. Is that clear? Like where I'm confused?
Um, Not fully. So
Okay.
these 3 pieces of information,
Hmm.
right? These 3 pieces of information are independent of one another because all three are needed by by the immediate manager, right?
Yeah.
So so when calculating my subtree min, I don't care about whether I am a BST or not, and whether
No, that
I'm.
is okay.
Hmm.
I understand that. I think so. In the BST question, it clearly says that the node value should be strictly less than the subtree max and the subtree right? That's why in this condition for is valid, we have strictly less than and yeah, right? It's not equal to.
Uh-huh. Oh, so
But
you're
when I'm
you're saying
yeah,
why
it's
not
like
replace this
yeah,
with
that can be node as well, right? Because we are while calculating that min
no, no,
right.
I still didn't get it. What do you want to replace this by?
Okay, so there is min, right?
So if I just quickly draw this here, we have, let's say I draw the left in green and the right one in blue, and I mark the root nodes. So in this picture, if I want to find my subtree min, I would take the min of this, the minimum value in this entire left subtree, and the minimum value in the entire right subtree. That would give me the overall minimum value in my
Yeah.
subtree. Same thing for max. Now to figure out if I am a binary search tree, I want the search property to apply at this level, right? That
I see.
means these
So that is
wedges.
local. Okay, so
Yeah,
here
that's
we are
local.
looking at the local
Yeah.
maximum and
And then
minimum.
what's happening inside these two subtrees, that is, I don't
That's
care about
local.
that. I want my
Mhm.
subordinates to tell me that information.
Okay, got it. Yeah. So here we are looking at the local minima and maxima, and then while checking validity, we are looking at the global max and
Yeah.
min.
Yeah. But when we say local, we are not comparing necessarily with this value because there can be, I mean, all of these values on the right side are supposed to be bigger. But even if
Right.
I go down here to this value, that should also be bigger
Right. So
than,
subtree min. Right.
yeah, so
Sub.
we want the
Okay.
minimum value in the right subtree.
Okay. Yeah. Thank you.
Any other questions? In the last question, why are we not returning local max? Why do we need to return my path sum? I think the same, the answer is the same as the answer to the question I think you had asked for an earlier problem. Why are we returning uh, my path sum? Because we got my path sum. We got the maximum path sums of this kind from the root downwards for the two subtrees under us from our two subordinates. So we have to generate that answer for our immediate manager. We could be the left child of our immediate manager. We might be the right child of our immediate manager. We don't know if we are, at our level, whether we are inside uh, this function call from our immediate manager or this function call. But for our subtree, what is the path sum? That is something we expect our manager to ask from us, just like we asked from our subordinates. So the return value here, this value is always in all 8 problems we've done today. This is for satisfying the manager. Okay, this is not for solving the problem globally or locally. I mean, of course, we need this to solve the problem globally or locally, but indirectly. Because without this information, our manager cannot construct their local solution, which may contribute to the global solution. But this is more like raw material we are providing to our manager. This is the actual answer we are computing at our level and tapping into the global answer to update it. Right? So in all the problems we are doing here, this return value has, that's why there are two different tasks. That this particular task and this particular task, these are two different values that have to be computed. This value is to be passed up in the boundary walk. This value is to be used to update the answer in the global mailbox. But without doing this correctly, these two variables that we are getting, they won't have the right answer. Even though we are not generating the right answer for our children, we are generating it for our manager, but everyone's executing the same piece of code. So our two subordinates will be, when they are returning from their function calls back to me, these two variables will have the correct numbers. That's my assumption. Now, if your question is why aren't we also returning the local max as an additional return value, that can be done. You can pass up the local answers along the up the tree, but it doesn't have to be done that way, right? This information is critical to pass up the tree because without it, the managers above cannot compute the answer. But returning the local max up to our manager is unnecessary because so the only goal there is the manager is going to take it and then pass it further up, right? Maybe combine it, compress it with the answer coming from the right hand side and take the bigger of the two and pass that up. But that same thing can happen outside, inside that, I mean, in that global mailbox. It doesn't have to happen inside the company, right? The managers don't have to be involved in doing that. Does that answer the question, Dhanashri?
Yeah, it does. Actually, what I was doing different was in the post-order DFS work, I was trying to find out what is a left sum by doing the addition of node val and the left node val and the right sum as like node val plus right node val. So I had those sum and I was trying to compute what is my max path sum. But I guess with this it's a different because we are comparing max path sum as a maximum of the node val and left sum path sum. So I guess how I tried to solve was a bit different than this approach. Um, I think
Okay,
I
so
need to combine.
you solved it before, I assume, like before outside of
Uh,
this class.
no, I didn't. I was just trying to find out how I can do it while we were
Oh,
discussing, and that's how I, tried to solve it. But I think I need to compute it to find if my approach would give the answer, or it would give something different answer.
yeah. So basically, in
I
this
think
diagram,
the approach you discuss makes more sense, and that is a correct approach.
yeah. So in this diagram, there are two things we have to calculate. One is the max path sum, right?
Mhm.
Which is our total answer. The other is we are expecting this kind of information to come up from our subordinate. So we have to calculate for this subtree, which of these is the answer we need to pass up to our manager. So calculation of this and calculation of this,
Mhm.
those are the two separate tasks. This thing has to be passed up. This thing has to tap into the global mailbox.
Right, right.
So it seems like you had missed, like instead of three, you said you're doing two of these left path sum
Uh,
and
I can put my solution. I can just write the piece of code that I was trying to do.
okay.
This is what I was trying to do. Instead of just after the post order DFS work, in order to calculate my path sum, I was doing this one.
Was this the last problem or more problem? Yeah, this is the last problem. So we are done. I'm just taking any final questions before stopping. Yeah, if you want to leave, you can leave. Is there going to be any session on strings? I have already taken sessions on strings. So those recordings are, I think, from maybe 3 years back, 3 to 4 years, 4 years back, I think. So those were recorded in this online format. Um, so they're not asking me to do that again. The trees series was taken in a classroom setting, so the recordings were not very, uh, they were not clean, and plus it was during my first year at IK, so I had just uh, started developing these patterns and my train of thought, so it was not very systematic. So this time I'm doing it in a more systematic way. These patterns are also more, they're a little different from what I had done that time. So hopefully this will come across as an improvement. Left sum is node dot val plus node dot. Oh, okay. No, yeah. So you're not going down. You're just taking the values at your node and then in your child's. Yeah. What about recursion? There's no series on recursion. Plus, I mean, I'm happy to take more DSA classes, but the the thing is, I have to do what the company wants me to do. So if there isn't as much demand from from business point of view for the company to have me spend time on DSA, then uh, that would be a limitation. So if you need more classes on it, you should be maybe asking Soham or someone uh, to have more classes on any topics that you find missing. Why was there no announcement about last week's session on Discord? I have no idea. I did, Ayushman knows that there is a session every week. So uh, maybe, I don't know, maybe he set up the class, or maybe I told him the topic a little like closer to Thursday or Friday or something. Maybe he just forgot to put it on Discord. I'm not sure. But there will be a class every weekend for the next 3 weeks till we complete the trees series. And then after that, at least I'm being asked by Soham to, move on from DSA. So if you need more classes on DSA, he and Shashi are the ones to convince. Okay, so seems like all questions are answered for today. So we can stop now. Thank you all. See you next weekend. After the series for trees, I'm not sure. They may ask me to look at some of the AI courses. Um, but that material may not be for alums. For the last 1 year or so, what I'm doing, in fact, last 2.5 years, the content I'm making has been for alums and people in the support period, not for individual cohorts. So it's not clear that I would be taking classes for alums after this, uh, but it's still being worked out. So if you need something, this is probably the time to bring it to the notice of operations and so on. All right, thank you. See you next weekend then.